As we all know, monsoon play a crucial role in shaping weather pattern, impacting agriculture, water resources, and overall climate stability. Thus, understanding and predicting monsoon behavior, particularly its extreme, still remains one of the most significant challenges in climate sciences. So, now to begin with our session, I would like to invite our chair of the session, Dr. Nico Caltabiano, on the stage.
Dr. Nico is an esteemed oceanographer currently working with the World Research Program. He has been instrumental in advancing critical projects such as subseasonal to seasonal applications for agriculture and environment, polar coupled analysis and prediction for services, as well as integrated prediction for precipitation and hydrology for early actions. In addition to his works on these vital initiatives, he has extended his expertise to tropical cyclone probabilistic forecast products project and data simulation and observing systems working group. We are fortunate to have you, Dr. Nico, lead this session, and we look forward for his valuable insights and guidance throughout the discussions.
Thank you very much. Welcome, everybody. Good morning, good afternoon, good evening, whatever you are. Thanks for those joining online as well. We have an exciting session this morning on the theme of simulation and prediction of monsoons, including extremes. We have 3 invited talks, all of them from colleagues in the United States. So it's quite late for them. So we'll try to keep on time, particularly those first talks. And then after that, we have 3 or 4 presentations here in Pune. So without any more delay, I would like to welcome Dr. Shukla from George Mason University. He doesn't need much introduction with his expertise and all the input that he has given to monsoon research over the years. So, Dr. Shukla, you have 20 minutes, including the questions and answer session. So I'll give you a warning in 5 minutes to go for you to wrap up, and then we have time for questions here from Pune or those online. So we can see your screen. If you can put your slides in presentation mode, so for a full screen.
I don't know how to do that, but let me try. Let's see. If I go to if I start sharing, I have no idea.
You are sharing the screen. If you go just down where you see notes, there's an icon. Yes. Just a little bit to the right.
Yes.
A little bit more to the right, then you see an icon of a screen share. The next one, and next one, next one. That's one, yeah. Perfect. So you have 20 minutes. Go ahead, please. Thank you.
Okay, very good. Thank you. Thank you very much. Thank you, Krishna, and thank you, Raja Gopal. Krishnamurti is the senior author of this paper, and I think structure and variability of monsoon rainfall can be described by 4 big changes. One is the seasonal cycle, of course, which we know very well that it is because of the northward propagation of SST and sun. Together, they give a seasonal cycle. But then we have a day-to-day fluctuations, which we call, if you remove the annual seasonal mean, we start getting what we call active and break cycles. And then we also get interannual variability. It could be year-by-year variability, and there has been a lot of work on ENSO and IUD and what is caused by ENSO, what is caused by IUD. Just look at the lower curve just for the IUD, and you see there are too many red lines in the next 60 years and too many blue lines in the first 60 years. Just keep that in mind, okay? So the purpose of my lecture is to give a kind of a unified description of all these variabilities by just one analysis, okay? And what the method we'll use, which is Krishnamurti has been using for a number of years, is called the multi-channel singular spectrum analysis. And what you find is that the first 6 dominant modes of this analysis, first 6, there's nothing done, no filtering. and no pre-screening, nothing. Just simple MSS analysis of raw data over India for 121 years, daily rainfall. And there are 6 modes will appear. And the purpose of my talk is to be able to describe these 6 modes in terms of all the factors that we just showed. Okay. So, and those of you know already MSSA, I don't have to tell you, but those who don't, I can't explain in 1 minute I have. But the important thing is to remember is that in this, you can go get both persistent modes, which are persisting for the whole season, and oscillatory modes. And oscillatory modes are sort of recognized by nearly equal singular spectrum analysis eigenvalues. And that there are very small difference between them, and their principal components are in quadrature, so they give a phase propagation. This is the mathematics, you know already. Just look at this. The mode 1 and 2 are in blue. You can see how close they are because the 2 eigenvalues are very close. That gives you the 45-day oscillation. The mode 3 is really the persistent mode. You see in red, it's just persisting. That's the ENSO mode. And mode 4 is the IOD mode. And mode 5 and 6 that you see in the green is another oscillatory mode, which we call, say, 28 days. Now, you may say, I just did the analysis. How did I give these names? Well, I'll tell you why I gave these names, because that's really the key point of this presentation is that these objectively analyzed modes naturally give us all the questions we have been asking about intraseasonal variability, active break cycle, and so IoT. This is so these are the outgoing. So by the way, it's done both for all India rainfall and also for the OLR. The first two modes. Just see the first one. It's a very clearly defined northwest to southwest tilted mode, which sort of propagates in the northeast direction. And mode 2, ISO 2, which we call it, is basically not mode 2, ISO 2, which is we call the, you see it has a quadrupole structure. So you can see that both have different structure depending upon what data you are analyzing. And by the way, look at the time series of each one of them. The blue one is ISO 1, which has clearly a period of 45 days. Red one is ISO 2. It has a time series of ups. How come it's not going up? Okay. Ups. Okay. By the way, if you look at just the rainfall over India and the OLR, which is a much larger region, you can see that the structure of our India is quite consistent over for the OLR. So basically, since Indian data is only over India, we don't know the whole structure, but it's very consistent. Both analyses give you very consistent result. And this is important because later on, I will use this consistency between OLR and Indian to be able to get a 120 years of larger structure from here. They propagate. You can see that. So just like you have in the when you have to do or MJO analysis. By the way, I personally prefer that MSSA is a much better method because if you're interested in the structures which are having time variation and both the space and scales you want to get together, because in UF analysis, you get the UF maximum variance, then you go and look for its time scale and find out what it is. Here, you get them together. Oscillatory modes are basically nonlinear oscillations. They are not perfect oscillations, but you can see the propagation. So if you take all the ISO1 and ISO and sum them together, and the whole phase, 360 degrees phase, then plot this, that's in the green, and they plot the actual rainfall of the whole 121-year period, periods of above and below 1 standard deviation. Look at the similarity between the observations and ISO 1 and ISO defined. Now, look at each year by year. So this one for 1972, there are three curves here. You see the red one is the ISO 1 and 2 together, and blue one is ISO 1, and the black one is the total rainfall over India. The reason I want to show that is because you see the orange dots. Orange dots are the points where the India Department definition that Rajivan started calls active and break cycles. We are proposing a different definition of active and break cycle. We are proposing that simply the phases of these ISO 1 and ISO 2, and you can see a lot of similarity, except that it is objectively determined and it is actually, you can then understand this, try to understand what it is. Okay, this is just a composite of the active and break. If you do no analysis at all, you simply take one standard deviation of all India on the left side, you get these active and break. If you do the ISO 1 and ISO 2, you get this on the right, two pattern. If you take the India Meteorological Department definition, you get the bottom two. You can say, I think that you can see that because of the artificial definition of the India Meteorological Department active and break, you get a very limited domain activity. Now, let's plot the 121-year cycle values of the sum of ISO 1 and ISO 2. That's in the red at the left side, okay, ISO 1. Good. The point is it's nearly zero average, okay? Seasonal mean is nearly zero. Bottom one is ISO 2 average, is nearly zero. Black one is the observed. On the right-hand side is the correlation between ISO 1, 2, and SST. This is a daily correlation for 121 years, nearly zero. Anyway, so the point is that these ISOs are not related to the global boundary conditions. They are completely natural modes, that's my conjecture. By the way, a paper that has been submitted, in case maybe one of you are reviewing it, this is the number of active and break days in case you have with and without the seasonal cycle. And you see, if you remove the seasonal cycle, there's absolutely no difference between the number of active and break days. So that's an important point to keep in mind. So what is the summary of till now? One is that this is an objective definition. They don't contribute to seasonal mean. And therefore, our conjecture is that it is a internal dynamics mode. All right, what about the other mode? The mode 3 and mode 4, okay, which I refer. Let's now, by the way, once you get that mode, then you can project that, get the PCs, project it on the daily data, then you get 121 years of data. Now you calculate UFs of that, and this is what you get. Look at the left side, is the ENSO, what we call mode 3, that is the ENSO mode. Why we call it ENSO mode? You can see it's not projected all the way because OLR was not available, but you see that's the ENSO response. On the right-hand side, the correlation with SST. You can clearly see ENSO on the right-hand side, related with that mode. Bottom is, we call it IOD mode for a simple reason, is that if you look at the structure, you get the dipole, and look at the SST on the right side, and you see clearly a dipole structure here in the Indian Ocean, very different from the ENSO mode. But the important thing is in the middle. Look at the two modes, ENSO and IOD on the upper curve in the middle. They don't come in the same phase. Some are in the same phase, some they are opposite. You know, we always have this mystery about, oh, why this year it was a drought, this year it was a flood, ENSO was causing this thing, IOD was causing this thing. When you sum them up, then only you get the total rainfall. And look at the relation between the total rainfall for these 20 years. Pretty good. I'll show you actually correlation for 122 years. So this is, so this is the same slide. I just wanted to tell you that individually IOD and ENSO modes are not necessarily in phase, but together they are very close to each other. Together they explain the total thing. Let me show you this. The actual correlations of these modes with SST. Look at the top one. IOD mode has a clear signal in the Arabian Sea, Indian Ocean. And ENSO mode has a clear signal in the Pacific. So this is the reason we call them ENSO mode and IOD mode. Now, if you take the correlation with the SST combined, look how similar it is to the observation. So they fully explain what goes on in observation in the total SST pattern. And this is the most interesting part. And by the way, so you can get it both the modes, also the corresponding rainfall structure over India, and you get day by day, sort of, and then you get the seasonal mean rainfall of total. That's in the bottom line. But there are too many curves here, so I've just taken this one in the second diagram. Look at the correlation between the actual rainfall obtained by the IOD and ISO mode over 120 years and the observed rainfall. The correlation is 0.83. I don't know of any other sort of derived quantities which had actually a correlation of which were that high. So these were the two parts. Now let's talk about the third part, which I talk about the epochal changes and multi-annual variability. This is just the raw data. And just please remember that the trend, so-called EMD trend, is sort of a very good technique of calculating trend. But you can see the observed rain 11-year mean. You can see the trend. So there's definitely Indian rainfall went through this epochal changes. You see the big change around 1960 in this. Whereas ENSO and DMI had, of course, trend because no trend was removed from the data. But here is the most interesting part in the lower curve, the upper curve you already see. Look, the IOD mode went through a major sort of change in the 1960s. Thus when, so the important thing that I have been telling you till now is that the total seasonal rainfall in any season will depend upon the combined effect of the ENSO mode and the IOD mode. And now let's break the data into two pieces, 1900 to 1960, and then 1962. And well, actually, I'll come to this later, just 1 second. This is what happens, you find. So look at the upper curve, 1901 to 1960 and 1961. ENSO mode is not very different in the two 60-year period. That's the main point of it, okay? All the calculations are done, just exactly it is, but just look how similar they are. Look at the lower one, the IOD mode. Look at the Indian Ocean, and it's completely opposite from the first 60 years to the second 60 years. Okay, so I think this change in the IOD mode is really a major factor in the epochal and multi-decadal variability. But I think that I skipped some of the slides. I want to go back. You can calculate these modes day by day for every year. And we have done that for every year. And I'm just showing you for 1997. And what do you see at the top curve? The ENSO mode was giving a negative rainfall all along for the whole season. IOD mode was giving positive rainfall. And as many of you remember, that actually happened to be a normal year. And we have always been wondering why it was normal year. And I think we know that because both, and this result has also been supported by a numerical experiment that has been done by Chulsu and Huang, that if you correct the SST in the Arabian Sea, you get that. Okay, so now we have shown you all the three factors. So I really want to leave some time for questions if people have questions. So let me just give the summary. I already gave you a summary of the oscillatory modes in the beginning, okay? This is the summary of this persistent mode that ENSO and IOD mode together explain the highest amount of variance, correlation of 0.83, okay? And so it's not, because we have too much emphasis on ENSO and ENSO response, but it appears that we really and the model, this is where comes the question of modeling. Our models have a real problem in getting the Indian Ocean SST right. And that is, so long as that happens, we will continue to have this problem of having incorrect prediction of summer monsoon rainfall. By the way, the essence of my first part of the talk was that intra-seasonal variability is extremely important for day-to-day weather prediction. But in order to do the seasonal prediction, we must get, first of all, these SSTs correct. Well, before the SST is correct, we must remove the systematic error. So, I mean, that's the biggest problem. So these are the challenges now in prediction of seasonal mean. But we must get both modes right. Just because you get ENSO mode, by the way, look at CFS. CFS has a great result from ENSO. It's a terrible simulation of IOD, and you get some. Okay, so it is these changes that have produced the epochal changes, and we must get both of them right to be able to make useful, successful seasonal prediction. And if there's time, I'll be glad to take any questions.
Dr. Shukla, thank you very much for the excellent presentation. We have good time for 2 or 3 questions here. I would like also to take questions online, so I encourage everybody to put your questions on the chat. So I have quite a few. I'll come to you, Krishnan. Andy, please.
Okay. Hi, Shukla. Andy Robertson here. Thanks for the fantastic talk.
Oh, hi, Andy. Hi.
It very much reminded me of a very similar study we did in 2012 with Vincent Morin and Michael Gill. You probably know the paper. Did MSSA of OLR and winds over South Asia, actually year round, without any filtering, without removing the seasonal cycle, nothing. And there we find also similar components with a modulated annual cycle that's modulated by ENSO IOD, things like that, although we didn't focus on that part. And then the ISO mode. But my question really was, in our study, we found that, you know, in order to get a highly anomalously, say, above normal monsoon year, you had to have the 2 things. You had to have the interannual part plus a rectified ISO. So it really mattered, you know, within the monsoon season, what the phases of the ISO were. So it sounded from what you said that basically it's cancelling out. But we found the opposite, that it's not cancelling out. And I think that's sort of also based on the previous findings from yourself.
It's cancelling out only in a seasonal sense. You are absolutely right. To be able to get a very big event, I think you are absolutely right. I mean, in this analysis, and by the way, yes, Michael Gill is really the one. We have to give him credit for bringing the whole MSSA picture. And I totally agree with you. I don't know why MSSA is not being used. So I don't want to underemphasize the need for prediction, intra-seasonal variability, but you can get a big progress in the seasonal mean so long as you get these boundary force, both of them correct.
Yeah, but what I'm saying is for the seasonal mean, you also need the rectified ISO. So, for example, in 1972, you know, in July, there was that huge break, and that's basically, you know, ISO, MJO related.
Well, look,
it had a rectified effect.
What you say makes sense, but I showed you the actual contribution of ISO 1 and ISO 2 of their seasonal mean year by year for all the 121 years, and it was not there. So we can talk about it later, but that's what our
Thank you.
Okay.
Thank you, Andy. Another question here? So before we go there, Krishna, you have the microphone if it's working.
Yeah. Hello. Good morning, Professor Shukla. Thank you for that excellent talk. This is Krishnan from IITM. Hello. I really enjoyed your talk. This is not a question, maybe more of a comment. So in the last slide, you are saying that the Indian Ocean is warming rapidly. And because of that, the ENSO and IOD influence on the monsoon predictability is becoming more complicating, right? Yeah. We heard a talk from Professor Bin Wang yesterday. So he was telling about how the ENSO has changed in the last century. And his point was the very extreme La Nina events are becoming more frequent, historical period. And his final comment was that it improves the prediction of the Asian monsoon rainfall, going somewhat with opposite with your message.
No,
So
but
I thought I will just
wait a minute. Improves the prediction in an actual model, or it improves in a?
not in the model. This is what he hypothesized.
Oh, okay.
It was a PNAS paper,
Yeah.
and so with Mark Kane and other group. So the main point he was trying is the El Nino characteristics are changing, becoming more towards more frequent La Nina events with increased predictability for the monsoon. That's a kind of hypothesis.
Okay. No, I think if there is a strong influence of El Nino or La Nina and it affects, it gets stronger. Of course, it will improve corresponding. What my Krishnamurti and my analysis shows is that the culprit for this epochal change is IOD for this long-term change, for year-to-year variability. But my main point was that we really have to have both correctly captured by our model if our interest is predicting seasonal, climate right now.
Okay, yeah.
But I haven't seen his paper. I'll look. I was hoping to join, but it was a very hard time, so I couldn't attend his lecture.
No problem. Yeah. Thanks, Professor.
Thank you very much. So we go to the last question here.
Hi, Professor Shukla, Subodh here. Very interesting talk. My question is regarding mode 3 and 4. So how they exist actually? Actually, if any mode we see, there must be some physically they must exist, right? So
and I showed you their structure. I showed you 3 and 4.
No, mode 3 and 4.
Yeah, mode 3 and 4 was ENSO and IOD, which I named as to be ENSO and IOD.
Yeah, in terms of rainfall, how they exist. For example, if you remove the synoptic events, do you get the mode 3 and 4? If you remove it from your data, their lows and depression, do you get the mode 3 and 4?
I have not done this experiment because you take the complete data and you do the complete analysis, and this is what you get. Okay. And by the way, I should say publicly that I owe an apology to Subodh. I have been telling him we have to get together and write a review paper, putting all these ideas together in one. And this has been going on for, but so okay, we will still do it. But these kind of experiments I haven't done. This is not a numerical experiment. This is not it is just a simple analysis of the raw data. And this is what you get.
Yeah, we agree with Miso. That is fine because if it finally cancel out, they have very small contribution, almost negligible. But the synoptics, the IMD, for example, if you ask IMD, if some year goes dry, you don't see lows and depression. Very rarely you see low and depression. Some year it gets excess rainfall, so automatically you get many lows and depression. So my assumption is that if you remove lows and depression from your analysis, probably this third and fourth mode will not exist. That's just my assumption.
All right.
Yeah,
That's
thank you.
actually that term, that what you just said is self-contradictory. I'll tell you why. What does really happen? What is meant by ENSO mode? Let's just talk about it. When you have El Nino, you have a large scale descending motion. Okay. So basically the point is that you have a seasonally persisting mode means there is a seasonally persisting descending motion. And in a seasonally persisting descending motion, there definitely will be less lows and less, because those are sort of the rest of the spectra. And if you have a seasonally persisting ascending motion, so the idea is not that they are not there, they are there, but they are not causing. That's the point. They are not causing the seasonal mean to be large scale ascent or descent. That's really the main point. So you can have a pretty simple description of the total as a combination of a seasonal mean, which is forced by a ascending by a persisting anomaly like El Nino. That's why we call it persisting mode, because that vertical velocity is persisting for the whole season. At least that's in an algebraic calculation. So in some way, it is more a conceptual point rather than a mechanistic point. Okay, it's a conceptual point in the sense that we are ourselves totally surprised, by the way, that how come the separation is so clear that if you remove the seasonal mean, then there's no difference between the droughts and flood years.
Thank you. We'll talk offline.
Yes, yes.
Thank you very much, Dr. Shukla. We could stay the whole morning here asking questions and discussing this interest, but we do have other speakers online
Oh,
to
yes,
give their
thank you.
presentation.
Thanks so much.
So thank you very
you.
much, Dr. Shukla. It
Thank
was
you.
good to see you.
Thank
So we move to the next invited speaker, Professor Zhu Wang from University of Illinois. Zhu, for those who don't know her, she is one of the co-chairs of the WWRP Working Group on Tropical Meteorology Research, which is one of the groups that organize the event here. So Zhu, the floor is yours. Let's see if you can share your screen and before we go ahead.
Can you see my slide?
Yes, can you put in presentation mode, please?
Okay, how does this look?
Perfect. Thank you very much. Go ahead, please.
Great, thank you, Nico. I will talk about the retreat season biases for North American monsoon in climate models. This work is supported by the NOAA MAP project and is mainly carried out by my former student, Jiacheng Ye. It has been published in Journal Climate in 2023. Okay. We know the North American monsoon is one of the most prominent hydrological features over Southwest North America. It resides between the Gulf of Mexico in the east and the Gulf of California in the west. These two regions represent two primary moisture sources for monsoon precipitation. In addition, as you can see in the schematic on the left, the monsoon precipitation is also modulated by tropical cyclones and easterly waves. So how do state-of-the-art climate models represent the North American monsoon precipitation? This figure shows the annual cycle of North American core region precipitation during 1979 to 2014. Here, the thick dashed line represents GPCP precipitation, and the thick orange line and the thick blue lines represent the AMIP and CMIP multi-model ensemble means, respectively. Also, the orange shading and the blue shading represent AMIP and CMIP model ensemble spread. You can see the orange line, which is the AMIP model ensemble mean, does a better job representing the monsoon seasonality. But the CMIP model has a larger shows a larger differences from observation. In particular, you can see in the retreat season in October, the CMIP models tend to overestimate monsoon precipitation, or they show a later retreat bias. We also examined the high-resolution CMIP models and the low-resolution CMIP models represented by the thin solid line and the thin dashed dotted line, respectively. You can see in the figure, they don't show much differences. Let's take a closer look at the relationship between model resolutions and also North American monsoon precipitation. Here's the y-axis shows the model nominal resolution, and the x-axis shows the North American monsoon precipitation. You can see the correlation is very poor. It's minus 0.1. In other words, model resolution has very limited impacts on the retreat season precipitation. So the question is, what causes North American monsoon retreat biases in CMIP models? In the following analysis, we will focus on this issue and also mainly in the month of October. Let's first look at the large-scale circulation anomalies. What we see here is the differences between AMIP and the CMIP model ensemble means. We have CMIP model minus AMIP model. On the left, we have 850 millibar geopotential height in shading, and vectors represent horizontal wind. You can see, compared to AMIP models, CMIP models tend to overestimate North Atlantic subtropical high and underestimate North Pacific subtropical high. As a consequence, due to the pressure or geopotential height differences, we have enhanced northeastward flow over the monsoon region, which brings more moisture and also leads to enhanced moisture convergence in the monsoon region. And that can at least partly explain the positive precipitation biases in the retreat season in CMIP models. We define a subtropical high index, which is the difference in 850 millibar geopotential height between North Atlantic and North Pacific. We have North Atlantic minus North Pacific, as shown in the two boxes in the top. This figure shows the scatter plot between the subtropical high index in the y-axis and the North American monsoon precipitation in the x-axis. The blue dots and the orange dots represent CMIP models and AMIP models respectively. We see a strong positive correlation between the monsoon precipitation and the subtropical high index. In other words, when we have a relatively stronger North Atlantic subtropical high and a weaker North Pacific subtropical high, the pattern tends to lead to a higher retreat season precipitation in the North American monsoon region. So the question is, what leads to the subtropical high biases? We used a stationary wave model developed by Mifang Ting and her colleagues to diagnose the subtropical high biases. The model is based on linear primitive equations shown on the right. You can see we have a vortice equation and also a divergence equation and a thermodynamic equation. The model can be solved for anomalies with respect to a specified three-dimensional mean state. And the model is forced by three forcing terms. We have diabatic heating, topography, and transient eddies. For the problem of interest here, diabatic heating is most important. And we are going to use this stationary wave model to establish the link between North American monsoon retreat season biases to regional diabatic heating biases. We first drive the model by the global diabatic heating differences between CMIP models and AMIP models. What we see in this figure is 850 millibar stream function in shading, and the vectors represent horizontal wind. And this is very similar to the difference between CMIP models and AMIP models, but we can also see some quantitative differences. The pattern on the right shows the stationary wave model response to global heating differences between CMIP models and AMIP models. Next, we want to investigate this question. What regional diabatic heating biases contribute to the North American monsoon-related circulation anomalies or circulation biases? We place the heating in different regions, as shown in the blue hatched boxes in these figures. And then we use the regional heating forcing to drive the stationary wave model. The shading here represents the stream function response in the different experiments. You can see when the model is driven by heating over tropical Northeast Pacific in the lower left panel, the response actually is similar to the response when the model is driven by global heating. We can take a closer look here. Here, the top panel shows the stationary wave model response to the global heating difference between CMIP models and AMIP models. And the bottom one shows the model response to the heating over tropical northeastern Pacific only, as shown in this white box here. If we focus on North Pacific and the North Atlantic, you can see the two patterns have the two figures show very similar patterns, although the response in the lower panel is much weaker. Okay. Now let's take a closer look at the heating anomalies over tropical northeastern Pacific. The figure on the left shows the heating profiles derived from EIE5 in dashed line. And the orange line and the blue line represent the AMIP and the CMIP model multi-ensemble means respectively. You can see the AMIP models represented by the orange line show a better agreement to EIE5. And in contrast, CMIP models tend to overestimate heating throughout the troposphere. And we also examined the scatter plot between heating over tropical northeastern Pacific in the y-axis and the precipitation over the North American monsoon core region in the x-axis. Again, we see a strong positive linear relationship. And also the response, the large-scale circulation response can be explained by the Masonal-Gill pattern. When we have heating over tropical northeastern Pacific, we would have raspberry wave response to the west of the heating, and also a raspberry wave trend pattern extending downstream over North America and tropical Atlantic. You can, if we zoom in over the lower troposphere, which is the lower panel here, you can see we have the stream function anomalies associated with northeastward wind, which would enhance moisture transport to the monsoon region. Okay, so we have linked the monsoon retreat biases to diabatic heating biases. Then the next question is what contributes to the diabatic heating biases? We used the CSM model to investigate this question. We forced the CSM model with specified SST in different regions. First, actually, we forced the model with global SST difference between CMIP models and AMIP models. And the top panel shows geopotential height response. You can see the pattern is very similar to the CMIP model and the AMIP model differences. And in the bottom panel, the CSM model is only driven by SST differences over tropical northeastern Pacific, or more specifically between equator to 20 degree north, dateline to 270 degree east. You can see the in the lower panel, the pattern is quite similar to the upper panel, but the magnitude is weaker. Briefly speaking, tropical eastern North Pacific SST biases plays a primary role in generating the retreat season biases, but SST biases in other basins also make a contribution. In addition to the biases, we also examined the future projection of North American monsoon precipitation by good models and poor models. We used the relative entropy to assess the model performance in representing the seasonality of North American precipitation, and defined good models and poor CMIP6 models. Then we examined the model projection by good models in the top and the poor models in the bottom. Here, black lines represent the present climate from 79 to 2014, and the red lines represent the future climate from 2065 to 2100. You can see in poor models, we don't see like larger differences, but in good models, the timing of North American monsoon peak season does not change much. It still occurs in August in the future climate, but the peak season precipitation is reduced, and the retreat season precipitation is enhanced. Or you can say monsoon retreat is delayed. Okay, a quick summary. CMIP models tend to have a later retreat bias in North American monsoon simulations, which cannot be explained by model resolution. Using model hierarchies, we found that positive SST biases in tropical northeastern Pacific can lead to positive diabatic heating biases. And through Matsuno-Gill pattern response, we can have that would lead to enhanced moisture transport to the monsoon region, and also positive precipitation biases in the North American monsoon retreat season. Okay, I will stop here. Thank you for your time.
Thank you very much, Zhu. Excellent presentation. We do have time for quite a few questions. I encourage those online as well to post your questions in the chat. We have one question here, please.
Thank you very much. I think you may have mentioned this, but did you look at the response to forcing the Northeast Pacific, or diabatic heating in the Northeast Pacific itself, and the effect of that? And I mean, a lot of those models have got problems with the stratocumulus cloud cover in that region. So I suppose I'm wondering, I mean, you showed a response of the subtropical high to forcing in the Pacific, but I suppose the other possibility is that you could force the subtropics. You could put the heating term, correct the heating term in the subtropics directory. Did you look at that?
Is your question about the clouds?
It's about the role of the Northwest Pacific itself in the biases.
Northwest Pacific.
Yeah, if you'd looked at the effect of having a diabatic heating term in the Northwest Pacific.
Yes, if you look at this panel here, you can see in this experiment,
Sorry, my mistake, my bad. I mean Northeast Pacific.
Northeast Pacific.
Northeast Pacific. The stratocumulus region.
Yes, in this experiment here, we placed the heating in Northeastern Pacific. It covers part of the stratocumulus region, but we did not examine whether the heating biases, like in this one here, is tied to you can see we have biases throughout the troposphere. We did not examine whether the heating biases in the lower troposphere is tied to any specific cloud type.
It's probably my fault because I'm sitting a bit near the back of the room, but I thought that box was the one in the tropics. Is that box? Is that box in the tropics, or is it in the extratropics? I can't see.
It's from equator to 20° north, so it covers part of the low cloud region. But we also examined further north. I don't think I have an experiment here. Yeah, I don't think I showed the experiment here. Maybe it's this one here. Yeah. At the heating in the further north, that also makes a contribution to the response, but I cannot say for sure how that affects the magnitude.
Yeah. Okay.
The paper has been published. Yeah. Sorry.
Okay, that's great. Thank you.
Thank you. Any more questions here? Any questions online? Nope. Any questions here in Pune? No. So, Zhu, thank you very much. Excellent talk, and I'll see you in Qingdao for the TMR meeting.
Thank you.
Right. So we go for our third invited talk of the day. Vijay Talapragada from NSEP. Vijay, the floor is yours. Let's just check if we can see your screen, please. If you can, you are sharing, I guess.
Yeah, can you see my screen?
Yes, perfect, and we can hear you well. Thank you very much. You have 20 minutes, and I'll give you 5-minute warning before we finish. Thank you.
Thank you. Thanks again for providing this opportunity to the organizers, IITM Pune and IWM workshop organizers. I'm sorry I was not able to make it in person, but I'm glad I'm able to at least join virtually, and excellent talks. And I would like to share some of the work that we are doing at NSEP, particularly developing the next generation global modeling systems, both for the deterministic and ensemble components of it. And we are almost there in terms of transitioning into NOAA's new unified forecast system that will replace the atmosphere-only global modeling system that we have currently. And we are evaluating the performance of the UFS in multiple facets, including what I'm going to present here today on the Indian summer monsoon evaluation. So the outline of my talk would be to describe briefly what the UFS is, how we are simulating the monsoons and evaluating them from different UFS prototypes. We will look into precipitation related to Indian monsoon and the UFS prototypes, and some diagnostic analysis, including the diurnal variation, and summarize the results. So this is the active development that's happening with the support from a lot of people from community and NOAA. It's a coupled unified forecast system applications for global medium range, subseasonal, and seasonal forecasts. What you're seeing here is a schematic of the UFS, which constitutes of different component models like the ocean model here, WaveWatch, that's supporting the wave component, sea ice, aerosols, atmosphere, which is driven by the finite volume cube sphere dynamical core, and the land model here. All are connected through a sophisticated mediator called the CMAPS, the community mediator for Earth prediction systems. And we developed this system for the last 4 years, and now we are actively testing and evaluating it for operational implementation. Most likely next year, next fiscal year, 2026, we will implement the next version of the global forecast system, the GFS, and the ensemble forecast system, the GAFS. And we're also replacing the age-old CFS, which IITM gladly also used for monsoon predictions for a long time. And that model was last upgraded in 2011, and it is time for us to move on with the new model that we are developing. And we want to call it as a seasonal forecast system because we don't necessarily do climate projections using the CFS. So it is a fully coupled UFS. We have ensembles that provide the means for uncertainty as well as the spread. So for GFS version 17, the goal is to increase the resolution from current 13 kilometers to 9 kilometers, and also improve the data assimilation, which is now going to be JEDI, which is the Joint Effort for Data Assimilation Integration, another community-based effort that has multi-agency partners to advance the data assimilation techniques. Right now, we are only using JEDI for non-atmospheric components like the ocean waves and ice and aerosols and land. Atmosphere, it's still work in progress. We will also retire some of the existing models within the NSEP production suite, but that's not necessarily what I'm going to talk about. So we have a set of high resolution prototype experiments to evaluate the coupled model performance, because this is the first time we are introducing the ocean, ice, waves coupled to atmosphere and land. And obviously, it requires a lot of development, a lot of testing and evaluation. And we have carefully chosen these prototypes so that we evaluate the model's performance, both scientific and technical, so that we can make progress towards implementation. And among those important high-resolution prototypes are the HR1 through HR5. C768 is 13-kilometer resolution. C1152 is the cube sphere at 1152 grids that is close to 9 kilometers across the globe. So those are the prototypes that we are finalizing. The final prototype is the HR5, which we have just completed. The results are promising, and I will share those results. This is what exactly the HR5 looks like compared to our operational GFS, which is the current operational system that is atmosphere only, 13-kilometer, 127 levels. We looked at both the June, July, August, as well as the winter season, December, January, and February. This is a scorecard. Those who are in the business of global model evaluation probably can easily understand. These are the anomaly correlation coefficients for various variables in various geographical regions, North America, Northern Hemisphere, and Southern Hemisphere. And you can see the triangles, the green upward, the large triangles demonstrate statistically significant improvements. And the improvements are out to day 13 for North American region or Northern Hemisphere, particularly for the winter time. And for the summertime, the improvements are pretty significant out to day 4. And sometimes in the Northern Hemisphere, the vector winds and temperature have significant improvements beyond the short range. So we are pretty comfortable and happy with these results. They're definitely in the right direction, positive improvements. And likewise, we are developing the global ensemble forecast system, which is another primary modeling system that we use for probabilistic predictions for subseasonal timescales. Again, the major differences between the current operational version, which was last upgraded in 2020, which is the version 12, is to introduce the ocean, the stochastic perturbations, ice model, and perturbations of both sea ice ocean coupled analysis. And we're also upgrading the vertical resolution of this model to 127 levels, consistent with the atmospheric model in the deterministic model. And we will have, for the first time, WaveWatch 3 providing a two-way feedback into the atmospheric model. We wanted to also include aerosol influence, but that proved to be extremely difficult, and we deferred coupling to aerosols to the next version. And we are actively developing the reforecast capabilities for the GEPS v13. And similar to the GFS, we also have different prototypes, which are named as EP1 through EP6, which are ensemble prototypes. And they are using replay initial conditions, which are replacing our reanalysis products. And the replay is using the European Center ERA 5 atmospheric analysis and ORAS 5 ocean analysis. Land also is replayed, but we are using our own in-house NOAA MP replay initial conditions, and the waves are coming from the GFS GDAS analysis. So some of the results, again, EP6 is the final prototype, and the GEPS v12 is the current operational system as the benchmark. And you can see both the anomaly correlation as well as the RMS errors. Substantial improvement, particularly out to day 10. These are, again, remarkable improvements. And you can see the die-off curves for the Northern Hemisphere, statistically significant improvement out to 264 hours and even beyond, which is unheard of in terms of how we made these model upgrades in the past few years. Looking at the MJO skill from the ensemble prototypes, the black is the current operational model, which is uncoupled. And there are two different versions of the coupled model here, EP4 and EP5. They are definitely better performed compared to the operational GFS, gaining about 4 to 5 days worth of skill for MJO, including propagation of MJO that was not so good in the current operational GEPS v12. The individual components of RMM1 and RMM2 also show similar improvements out to the day 35 as seen here. So that's the background on our prototypes, and I will switch to evaluating these prototypes specifically for summer monsoon. And we will be using different prototypes as mentioned here, HR1 through HR3A or 13-kilometer model, and HR3B to HR5 or 9-kilometer coupled model. EP5 is the ensemble coupled model prototype. And we are using the summertime of 2020 for GFS, and 3 years worth of forecast for the subseasonal using the EP5. We are using the GFS V16 analysis as well as ERA5 for verification of winds, and the precipitation we will be evaluating using CPC, CMARF daily and hourly analysis, and also climate diagnostics report, GPCP daily precipitation analysis. For convenience, we wanted to look at different indices that are currently popular in literature. They include the Webster-Yang Index, East Asian Index, Dynamical Indian Monsoon Index in 2 different regions. Likewise, East Asian West Northern Pacific Index. These are very well published in literature. So we wanted to look at all these indices and also look at the rainfall, particularly for these regions that are covered by some of these indices like the extended Indian monsoon rainfall, South Asian rainfall, Indian continental rainfall, as well as the Webster-Yang. These are the definitions for those who want to refer to. East Asian Western North Pacific Monsoon Index is based on the journal winds at 850. Webster-Yang Monsoon Index is based on journal wind shear. South Asian Monsoon Index is meridional wind shear, and Dynamical Monsoon Index is again, low-level journal wind differences in 2 different locations. So looking at the time series here, these are every day mean forecasts at day 10. This is the East Asian West North Pacific Monsoon Index. All the dotted lines are different prototypes, and the black line is the GFS analysis. We also use the ERA5 analysis with the open circles. That is, you can see that both GFS and ERA5 analysis are pretty consistent. That is confirming that the analysis is capturing this index pretty nicely. But you can see the HRs have different behavior than the observations. We have July 25th is the onset for the Eastern North Pacific monsoon during 2020. And the HRs were able to capture the onset and the increase in this index pretty nicely, although the magnitude is not as good as the observations. And compared to this purple line, the green line definitely did much better. That means the latest HR5, has better skill compared to any other prototypes and the operational GFS. Likewise, the Webster-Yang Index, not much difference except for initial time when we have some high bias, but otherwise the models are doing really good capturing the Webster-Yang Index for the journal wind shear. The South Asian Index, the operational GFS has a very high bias. The new prototypes from the coupled model actually more realistically captured the variation and reduced the strong bias for the South Asian Monsoon Index. This is the Dynamic Indian Monsoon Index. Again, all the prototypes have done very good compared to the day-to-day variability of the Dynamic Indian Monsoon Index. And the new HR5 is as good or better than the operational GFS for this particular index. So looking at the precipitation, again, 10-day lead time. Every 3rd day, we are looking at the entire summer of 2020 from June 10th to September 8th, actually. And we are using 2 different analysis data, CMARF and GPCP. And we looked at the variability of GPCP and CMARF. Actually, GPCP has somewhat higher precipitation relative to CMARF, which is not surprising, but definitely has some bearing on how the evaluation results in the skill scores. So before July 25, HRs show rather low bias or weaker precipitation. but after the monsoon onset, you can see the HRs are much closer to the CMORPH as well as the GPCP. Similarly, we looked at the South Asia, Eastern India monsoon rainfall. Again, there are reasonable variabilities captured by the prototypes, although there are still some overestimations before the onset of monsoon, and operational GFS definitely has very high bias, as you can see in the purple dotted line. HRs definitely reduced that positive bias, except for some days where they are not as good. So looking at the Webster-Yang monsoon index and also looking at the mean precipitation over that particular domain, the average precipitation as denoted by CMORPH is about 5.2 millimeters per day. GPCP is slightly higher, 5.5, and HR5 is much closer to GPCP than the GFS, operational GFS. Likewise, we are looking at the South Asian and East India monsoon rainfall, which is also suggesting that the HRs and the GFS have rather high bias, mostly in the pre-onset time period, which contributed to the seasonal mean bias much higher than observations. The Indian continent only rainfall, again, both GFS and the HR experiments, particularly the late July time period, have huge positive bias, maybe much closer to the GPCP than the CMORPH. But this really highlights the need for more accurate precipitation that is to be used for evaluating these prototypes as well as operational model forecasts. We would like to use the IMD derived precipitation data to validate these results, and that work is currently ongoing. Some of the spatial maps, the difference of the precipitation relative to CMORPH from the latest prototype, you can see that there are rather higher precipitations over northern India, but huge deficiency in terms of capturing precipitation in the Western Ghats and the southern continental India, which is probably typical of the low resolution models, and we are trying to understand what these are. And we also looked at the diurnal variation, particularly for week 1 and week 2. We have higher precipitation over the northern Indian region. Again, prominent deficiency of precipitation, particularly in the Western Ghats and the west coast of India. And this tells us that the continental rainfall, mostly due to convection, is still not captured by the low resolution global models, and we need potentially high resolution to get to those details along the west coast.
Can you wrap up? We have 3 minutes.
Yeah,
please.
I'm almost done. So the diurnal variation, again, that shows the reasonable capturing of the diurnal variation from the GFS, except that we have overestimation of rainfall, especially in the daytime, and in the evening time, they are much closer to CMORPH. But again, over midnight, it shows overestimation again. However, our ensemble prototypes pretty much are flatline. They don't capture the diurnal variation like the high resolution models that we have. So this is something that bothered us, and we wanted to understand why the model is not able to capture the diurnal variation as much as what we saw in our HR prototypes. Similar to the global deterministic model, we also see some of the deficiencies of the EP5, which is the ensemble prototype. In the interest of time, I will skip this and summarize the skill of or the ranking of these models, especially from the high resolution prototypes. These are the RMS errors for the Western North Pacific East Asian Monsoon Index and HR4. The last but one has the lowest RMS errors compared to any other prototype, which indicates that we are making good progress with simulating monsoon and associated rainfall and the large-scale synoptic patterns reasonably well. So this is my summary. I don't want to repeat what I said, but we definitely need more diagnostics and further evaluation. All the data sets that I showed here are made available on AWS for all our collaborators to download and look at or evaluate with their own diagnostic tools and verification tools. So we will be glad to collaborate with anybody who wants to work with us in exploring further the performance of these prototypes as we make progress towards implementing the next generation coupled model for operations. So I'll stop here and we'll be glad to take any questions if I have time.
Thank you very much. Thank you very much for all the work being done there. We have time for one or two quick questions here from the audience. And I encourage those online, if you have questions, please post on the chat.
Hi, Vijay. It's Hugh Lewis here at the Met Office. Thanks for the nice talk. There's clearly a lot of work goes into these model upgrades, and I wonder if you could comment on which of those differences you think are showing the most impact. So is it the resolution, physics, the coupling? Which do you think have been the big levers for updating the UFS performance? Thanks.
Yeah, that's a wonderful question. So as I showed, the progress from HR1 to HR5 is actually gradually adding the resolution, the physics changes, the coupling, the analysis. So we are adding incrementally each prototype. That means they are contributing, and collectively they are adding to the final prototype, not necessarily linearly added, but the biggest bang for the buck definitely came from resolution.
Wait, one last question here, Rajagopal.
Yeah, thanks, Vijay, for a nice presentation. I just wanted to know, you still showed a chart in which the precipitation over southern parts of India are still not very well captured in HR5 also. So how do you plan to improve that? Because you know the West Coast and gets a lot of rainfall, especially in monsoon.
Right. Thank you for the wonderful question, Dr. Rajgopal. These are day 5 to day 10. So I'm trying to look at the medium range precipitation forecast skills. Short range, they are not as bad, but as the convection, the parameterized convection definitely is not able to capture the spatial variability as well as the magnitude, particularly in the topographical regions in the West Coast. So I think we have to seriously look into increasing the resolution further and also potentially revisit how the convection is parameterized in these models.
Thank you, Vijay. We are going to move now for the in-person presentations here, and we are going to start to have fun with the bell. So the first in-person talk is going to be from Marion Mittermeier. And Marion, you have 15 minutes with us, and I'll give you 3-minute warning with the bell. Looking forward to it.
Right. Well, good morning, everybody. So we're going to switch gears a little bit, because I'm very much coming at this from an impact-based warning or forecast perspective. Thank you. And so it's a little bit different to the talks we've had so far. And we're primarily interested in how we can squeeze as much skill and predictability out of our operational models that we have at our disposal. So I don't really need to tell this audience about the Kerala floods that happened in 3 consecutive years in 2018 to 2020. What I wanted to really pick up on here is that there were individual days where there was a lot of rain, but what made these events impactful was the fact that they are compound events. That's the thing that really stood out for me. In other words, it was a sequence of successive days of heavy rain that led to the impacts and the obviously devastating impacts in some cases that these events led to. And that's really the thing that I picked up on in this analysis, is that we're trying to forecast sequences and not just individual days. So before we jump into the whole multivariate idea that sits behind this work, I wanted to just unpack some of the ingredients that we might be looking at involving in such an analysis. We have a coastline and topography, which is aligned perpendicular to an impinging westerly jet. So, and we have low-level sources of moisture. And this is very analogous to what we might see with atmospheric rivers that occur along the west coast of the US, for example. And so these are the ingredients that I'm going to look at exploiting and exploring in terms of how they combine to create the events that we saw, and if they combine to create the events that we saw. I'm using the global operational and deterministic forecasts from the Met Office. I'm using the analyses and GPM iMerge where I need to use that for the precipitation. And I'm going to, first of all, look at some of the bivariate relationships that exist over this area that's masked in pink on the right. And I'm going to try and eventually get to understanding or trying to answer this question: can multivariate feature-based approaches identify the potential location of the heavy rainfall that was associated with this juxtaposition of wind and humidity? And does it provide, or can it provide, enhanced predictability for events like the Kerala floods? And I'm particularly interested in the medium range, and the results I'm showing are all for the day 5 forecasts. So the analysis is underpinned by a community development based or sourced tool that is curated by NCAR, known as Met Plus, which we're about to operationalize as our verification system at the Met Office. And the first tool I'm going to exploit is a tool that allows you to look at bivariate distributions between different variables. And so I went around the different combinations and permutations to try and identify some of these relationships. And they plotted on the right. I don't really have time to talk about them in any great detail here. I want to tease out a couple of important points, though. The U wind, or the westerly wind component at 850 hectopascal, really demonstrates, or brings out this jet, the westerly jet, that's about 20 meters per second. And at the same time, that is really associated for these events, this 11-day window that I analyzed, which is just prior to and during the 2019 floods, that you can see that it's associated with relative humidities between 80 and 100%. The V wind, or the northerly wind component, I did look at, and usually is just north of west, so very small in size, and it does have a little bit of a signal, but we did not include it, as I'll say later. The largest rainfall accumulations were associated with the U wind at 850 of about 20 meters per second, and the largest accumulations are exclusively associated with relative humidity above 90% at 8050 hectopascal. It's similar at 700 hectopascal, and in the end, we preferred the 700 hectopascal field because we felt that, moisture at depth was really quite a crucial component. So the feature-based analysis tool that we use is MODE, or the Method for Object-Based Diagnostic Evaluation. And it's been around for some time and really works on trying to identify the features in a field which we're interested in and basically discarding the rest. We identify features by thresholding, then we can decide to smooth before we threshold. And the crucial bit is we put the original field information back into the objects. These objects you can create, you can identify in 2 data sets, and then you can match them. So you can find match pairs and you can analyze the match pairs as well. And that's really what we're going to be doing here. Multivariate mode is a multivariate extension of mode, which has a logic capability to investigate how, objects across different variables overlap. And these are then known as super objects. Any variable can be populated or used to populate the super object. So it doesn't have to be one of the input variables, if you like. And we used grid-diag to identify which variables we want to put into multivariate modes, and also the thresholds. And they are listed, as you can see on the slide here. And the key point is that we back down on some of the intensities, primarily because otherwise, you really don't give the algorithm much of a chance of identifying the overlapped super objects. So they may look quite modest, but they're quite important that you don't push the thresholds too high. So what we're trying to achieve, just in sort of a schematic form, is you've got individual univariate objects of the different variables that you're putting in, and you're trying to find this overlap, the intersection between them, and that's the super object. And you identify those in the forecast fields and in the analysis fields. And then your analysis can proceed in exactly the same way as you might do with a univariate process. You can analyze the attributes of the super objects. And that's what we do here. We're trying to understand whether A, we can identify them in super objects in the analyses. Then do we have a match in the forecast? That's really what we also want to know. Is there any kind of predictability? And thirdly, can we actually find whether the precipitation peak is in the super object? And so that's what we're going to look at. And I'm just going to try and illustrate this very simply with a sequence of the objects from the 2020 period. And I will try and explain as we go along. So there's lots of panels on here. The precipitation panels are all on the left. And the super objects, so there's two different kinds of precipitation objects here. There's the super objects top left, and then there's the univariate objects on the bottom left. And then we have the wind and the relative humidity on the right. And you have two panels each time. You have the forecast or the object, and then you have the analysis object. And in this instance, if we just look at the precipitation for a minute, you can see that there is some rain impinging on the West Coast in the univariate sense, which has kind of been removed from the super object in the panels above. And that's primarily because at that point, there is no interaction between the relative humidity and the U-wind component. Okay, so let's step through this. So we can see the increase of the wind strength approaching the coast, and we can see an increase in precipitation that occurs. And then we can see how this lingers over several days, and the precipitation, of course, lingers as well. And then eventually we can see that the westerly jet withdraws. There's a little bit of a reduction in the moisture, and of course the precipitation wanes as well. For the remainder of the talk, I will just be focusing on any of the features that we identified that had centroids within the rectangle that you can see on the slide. And here we're really going to just look at this idea of the sequence in the time series, and what does that tell us about the predictability of sequences. The top is the sequence of matched pairs, the areas of the matched pairs that we find from the super objects, and the bottom is from the univariate objects. And there are 3 seasons superimposed running along the axis there. And I'm only showing you July and August because prior analysis showed that this combination or juxtaposition of humidity and wind just does not happen in June. So, you know, I'm just showing you from July onwards. And if we just focus on the univariate objects for a second, you can really see that the onset of the monsoon, you know, in early July. And then you, in the univariate sense, you just basically have some sort of matched pair object virtually every day at some point in some way. And it's actually quite messy. So if you have to think about, well, which one of these events could be impactful, it's quite difficult to tell. Crucially, if we look at the super objects, the matched pairs, I want to just emphasize this. So there was the method identified the object in the analysis for in the windows that the heavy rainfall and the flooding then subsequently occurred from. And secondly, it found a match for every single, you know, observed object in the day 5 forecast. So that for me was quite a result. But then if we also then focus on the box here that we have, which denote the sort of time windows for each of the seasons, what we find is we actually have these sequences, and the sequence I identified was looking at longer than 3 days. And we have sequences in excess of 3 days for each of the 3 years and the events windows that we are interested in. It's important to note that there are a few such sequences earlier on in the season, particularly in 2018. And for example, so it's not going to be a perfect match between whether you have the object, you know, some event identification and the link to direct impacts. So, but that's not the point of this. We first have to identify the events before we can think about potential impacts. Needless to say, the method was able to capture this. So to conclude, I just want to pick up on a couple of things after having studied the three events quite closely. And I'm proposing some sort of a schematic or life cycle or, some sort of development, evolution and decay of what I would consider a quasi-atmospheric river episode, because it isn't really an atmospheric river, but it has got a lot of the same characteristics. And it really kind of starts by having that moisture reservoir, which is primarily to the south, and that then slowly migrates further north and gets bigger or more substantial, whilst we have the approach of a westerly jet towards the coast, and it gets closer and closer. And when these two then interact and engage and also crucially impinge upon the high ground of the Western Ghats and the coast, that we have the enhancement of precipitation, and therefore we can identify these super objects. And this can persist for several days. As I say, this is what we find. And then eventually there's the cessation, which is when the wind retreats or, the wind wanes and some sort of relative humidity, the pool of the moisture actually also reduces or just retreats somewhat. So this is kind of what we found from these events, and they all pretty much follow a very similar process. So this might be something we can explore. So that's on to what comes next. I think the methodology, the multivariate methodology, has identified and proven that there's a set of ingredients which might offer a potential predictability. I've just shown it at day 5. I think we should look beyond that, and that's certainly the plan with colleagues at NCMRWF. And my key comment or question and hope is that we can exploit this through post-processing to actually produce some products that can put this together. There's also the compelling idea that we might extend this to ensembles and make it more applicable to even longer timescales, to, sub-seasonal at least. So with that, I can conclude, and I thank you for listening.
Thank you very much, Marion. We have time for one question here. Marion is going to stay here for the rest of the day and tomorrow, so you engage.
Sorry, just a brief question. So you constructed the bivariate and probability distributions. So two are okay, but when you are going into higher distributions, then somehow you're handicapped by the way that you create the PDFs. So how much of impact did, in your experience, you feel about the results in terms of constructing these PDFs?
I don't, yeah, I mean, the process is entirely empirical. So you just go with what the data is. So you're not doing anything too statistical. You're just trying to get the data to tell you what there is. I use the bivariate, the two-dimensional histograms, to just understand some of the thresholds that we look at. And then I try to, I picked 3 variables to keep it simple, or as simple as you can. I could have left precipitation out, actually, but I decided to leave precipitation in, so that the multivariate part was done with precipitation, wind, and humidity. And it seemed, yeah, I was really, I suppose not necessarily surprised, but I was gratified that it worked as well as it did.
Thank you very much, Marion. For the sake of the time, we are going to move to the next question. Marion is going to stay here for the day, so please engage with her to ask the questions. So we are going to move to the next talk here. Julius Akniola. Is Julius here? Julius, are you online? Can you guys from the tech there check if Julius is online? He's online? He's not. Okay. So if he comes online, and then we move to the next one. So let's go to the next one, which would be Praveen Kumar Potapakula at ETH Zurich in Switzerland. So Praveen, you have 15 minutes. I will give you a 3-minute warning.
Okay.
Okay,
Yeah.
thank you.
Yeah, thanks. Yeah. Hi, everybody. Nice to be here. So I'll talk about some of the developments at ETH Zurich. And I work with Andreas Prine and Anurag Dipankar. And I will straight away acknowledge collaboration. It's okay. Straight away acknowledge the collaborations from our German colleagues in the development of ICON global model. And also extremely grateful to work with software engineers at Exclaim, where they try to refactor the code to Python, which I will talk to you about. It's really nice to engage with software engineers, but it's also sometimes a bit crazy because we are on a different wavelength. Yeah. Okay. So I show you some of the processes as a motivation across various spatial and temporal scales. And well, I don't want to go into the detail, you know, the process that occur, synoptic, convective scales, and so on. Well, the climate models usually operate around those at that particular sector. They are able to resolve synoptic scales, of course, a bit of cyclones and other processes. Weather models, we kind of downscale into high resolution. They can resolve deep convection and organized convection. And we also have LES to study processes. Yeah. So yeah, some of the examples: convective storms, organized convection, large scale signals, and so on. So at this point of time, what we need is really models that are able to provide local granularity to resolve mesoscale processes globally. So how do you do that? We want to push the global models from this resolution towards this scale. Now, how do we do that? With the emerging new hardware technologies, such as GPUs and heterogeneous architectures, we now have the opportunity to actually push our computational limits and push the climate models from this box towards this box. So in terms of computational infrastructure, I think we are at a breakthrough in climate modeling, not because of theoretical concepts or so on, but we are now able to resolve the processes explicitly with the computational infrastructure that we have. A little bit of kilometer scale efforts at Exclaim. Exclaim is extreme computing platform for weather and climate at ETH Zurich. Yeah, so now they bought, okay, we bought at ETH Zurich and other institutions such as CSCS, computing platform for Switzerland. So they have bought Alps supercomputer. It's a new one. So what it has is I demonstrate a simple super chip over here. So you have a CPU, you have a GPU, and they have respective memories. For example, the GPU has about 96 GB HBM, high bandwidth memory. And these are actually interconnected with NVIDIA Link, a high bandwidth cable which can share data very efficiently and very fastly. They communicate with each other. And then in the node, you have 4 such of super chips, and they all are interconnected with high frequency cables, let's say, for efficient data transfer. So these heterogeneous architectures, these chips which are coming or which are available right now are looking similarly like this. Yeah, but I'm not advertising for NVIDIA. But because we use NVIDIA chips, I just gave a sample over there. So what we can do is we can initialize the climate model on GPUs. And what we can do is to take the heavy computational burden or a part of the code in the icon and pass it to the GPU and ask the GPU to compute and take the responsibility to, push the code a bit further and give the result as soon as possible, as quick as possible. Yeah. So a little bit of what we have. We have about 2,688 nodes. And as I said, so each node has 4 CPUs arranged, and then totally it comes to about 10,000 GPUs. Yeah. We also have other processors, but yeah, we are as a weather and climate platform, we are using NVIDIA chips. So a bit of motivation. I showed the number of nodes. On the x-axis, the simulated years per day. On the y-axis, and we start from the left. We have a 20-kilometer simulation. We have used until 500 nodes. You see, this is a CPU simulation, and we can get about 2 simulated years per day if we use about 500 CPUs. If we use GPUs, and PY stands for Python, I will explain what Python is and how we translate it a little bit briefly in the next slides. But if you push to GPUs, you get a computational throughput of 1 simulated year per day as an advantage. So it's quite nice to push from CPUs to GPUs. If I increase the resolution from 20 to 10, you have about 2 simulated years per day, but then you see the scaling just flattens out when you are at 1,000 GPUs and 1,200 GPUs. Yeah, if I push it further to 5 kilometer, the scaling is relatively poor, but still we could end up at 0.5 simulated years per day. But mind you, we have not optimized the Python code. So without optimization, we get about 50% of leverage. So with optimization, we want to push it further. But one important note is this is an old system. I did not show you the scalings of the new system because we are testing it quite extensively. And we really want to showcase that we are better than this at about 4 or 5 times. We already achieved 3 times and we are kind of optimizing it. Yeah. Yeah, GPUs are more energy efficient because these are quite expensive simulations. You can't just burn the world by just using 1,000 or 2,000 CPUs. We also need to think about efficiency. So yeah, it feels good to also think about energy efficiency in this case. Yeah, so because of this emerging hardware technologies, what we really need is new approaches for climate models, and so that we leverage this HPC architectures. So I demonstrate a simple code here. Let's say we want to solve del psi on this grid. This is an icon grid. These are triangles. We want to just compute del psi. So if you kind of disguise it in a simple way, C1 refers for the cell 1 and C0 refers to the adjacent cell. You differentiate both and you divide by L. And if you want to code it, for example, this is a simple Fortran code. This is straightforward implementation. What you do is you go from JK loop, JE loop, JK to the vertical direction, JE to the horizontal direction, and then you kind of implement the formula. This is simple, but when you want to leverage parallel computation, then what you do is this one. So you open an OpenMP directive, you open an OpenACC directive, and then you optimize it, and then you put all the code over here with all the do loops, and you end the do loop. And then what you do is also end the OpenMP and OpenACC directives. Then what the software engineers do is to optimize these to the hardware infrastructure that we are computing upon. But sometimes, scientists and performance engineers are working on the same code. It's kind of an ugly code if you really see it. Sometimes the scientists are the performance engineers. We are also uneducated a bit in terms of performance, but yet we learn and we move forward. But we are at a crucial juncture in the climate modeling. So what we want to do is we kind of want to separate these concerns. We want to leave out all these optimizations at the back end to the software engineers. And we just want to worry about the front end where we are worried about the equations that we discretize. So we came up with a solution called as a domain-specific language, where we kind of use simple Python embedded inside a domain-specific language. And what we do is we generate a simple field operator over there. And what we do is define a function. We want to have a psi as an input and L hat as an input. And then what we do is ask to give out return psi of cell 1 minus cell 0 divided by L hat. So if you can look at this line, is just one simple line that you can see in the front end of your code. At the back end, the software engineers will take care on how to really optimize this and how to convert this code into C, C++, and then worry about the OpenACC declaratives, optimize it, and so on. So what we are doing is trying to separate the concerns out and trying to utilize as much as computational resources as possible. Yeah, a quick, so we started with Fortran code completely, and we are moving towards completely Python framework. What is also of our advantage is we can also imbibe workflows, for example, how you transfer the data, post-processing in Python, and so on. So we want to be in a complete Python world from start to zero. Yeah. So that would be really nice, but then we are a bit far. Right now we are here. So we managed to port DICO into the Python stencils, and then we did a lot of test experiments. Yeah. So the takeaway message is, yes, we are moving, the field is moving in a way that we are using DSLs now. This is a simple aquaplanet experiment. Sorry, there are no monsoons there because the sun is not moving around in terms of this direction. But what I show is 40, 20, and 10 and 5 kilometer. These are the low-level clouds. And quickly, if you can notice there, your low-level clouds are actually decreasing as you increase the resolution. By the way, we switched off the convection for all the simulations, and this is kind of demonstrated there. We have height and we have cloud cover, and this is the lowest resolution and this is the highest resolution. As you increase the resolution, you see the clouds are actually reducing. So this brings to the question, like, are the cloud microphysics turbulence schemes that we use, even at kilometer scales, ready for kilometer scales? Because of course, we want to eliminate deep convection, so on, as a parameterization schemes, but we also need certainly other parameterization schemes. The question is, are they ready? And so we are investigating this question. A little bit of simulations that we have done. So what we did is a series of simulations from 80, 40, and 10 kilometer. So we did 10 years of test run with Icon for 10 years, for 10 kilometers. That was a huge data, by the way. And now we are pushing towards 2.5 kilometers. Briefly about the configuration, we used Icon and WP, as I mentioned before. We used a simple Terra configuration. And we, as I said, so we kind of simulated for 10 years with an error 5 initial state. And then we prescribed monthly SST. It's not a coupled model. We are Python, the infrastructure is not there yet. So yeah, the convection is switched on in all the schemes. So I will show some little bit of monsoon results. So what we did is we applied a simple definition from Wong, the paper from 2008. What I show is the difference between local summer monsoon minus winter precipitation, and then which exceeds 2 mm per day. And also the summer at least contributes 55% of total annual precipitation. So what you end up is, with this figure, the icon 10, 40, and 80, you see the monsoon domains are captured, at least in the mean state. And this is comparable with observations. Of course, there are some exceptions. For example, the overestimation in the spatial extent over this particular region. In MSF, we don't see it, but with iMerge, we see it. So we also have observational uncertainty. Yeah. So it's kind of nice. Like you have a global model at 10 kilometers, and then you look at global monsoon system. It's nice. Even at 2.5 kilometers, is a great opportunity to actually investigate it further. Now, coming to the biases. So I will concentrate on briefly the Indian region. So you see, we have a wet bias in the monsoon core region. I was a bit surprised. You have a dry bias, I think. Then we have a dry bias over the Bay of Bengal and the Arabian Sea. Almost with respect to the resolution, the biases sign at least stays the same, but the biases somehow are amplified at 10 kilometers. We hope that at 2.5, we get it better. And more or less, we have wet bias in the northern hemisphere land and ocean. And over the land in the southern hemisphere, we have dry bias. So we want to investigate why this deviation happens in the northern hemisphere, in the southern hemisphere over the land. Yeah, 2 slides. We also looked at the probability distributions. For example, over the Australian monsoon region, you see that the red line and the black line, that means the high resolution, and the black line, the observations, they agree well. But of course, I mean, it also depends on which domain you see. So I don't have time to go through it, but it's not that simple that you have high resolution, it improves everything. It depends on what you look at. This is the diurnal cycle. I will focus on the right one on the interest of time. So of course, the model overestimates. Keeping that aside, look at the peak. So the evening peak in the iMerge is well captured in the simulation. So we were happy. But then this is the mean value. It's really unfair to judge from it. So what we did is to have a spatial look into the diurnal cycle. We have an evening peak over the land. You have a morning peak over the ocean. Of course, there are exceptions, but you see the 10 kilometers nicely captured such a phenomenon. Of course, what are the exceptions? Of course, the Himalayan region, where we have an early morning peak. This is also there in the model, but then it's actually moved to south. So maybe at 2.5 kilometer, we hope that we resolve such an issue. And we also have afternoon peak over the Bay of Bengal. We have to investigate why that happens. Yeah. So I can show some promising results. At the end, we have this nice animation. We have a tool that tracks all the systems, MCS, tropical cyclones, and so on. We are trying to parallelize it on GPUs, and we want to use it on icon data so that we go into process-oriented mode of understanding. Yeah. Thank you very much. And I have highlighted the conclusions at every part, so it's fine. I hope this plays. No, it's okay. It's a nice animation, but yeah. Thanks.
Thank you very much, Praveen. Impressive work. We have time for one or two questions.
So I guess with this one, then it looks like you've rewritten the source code, the Fortran source code, entirely in Python. I guess what some other folks have been doing is instead having automatic code translation, source to source, to map the Fortran code to automatically put in the parallelization and so on to the Fortran code directly, like with DACE or Cyclone that the Met Office are using. So could you say a bit about why you've chosen to rewrite in the Python and maybe the advantages of doing it that way? Or
well, I have heard about those, but I can only speak of the advantages of what we have right now. So at the end, as I said, so we want to be in a Python environment where we also want to imbibe workflows inside it. So computation is one aspect, but the workflows are kind of challenging right now in terms of post-processing. How do you handle the data? So if we have such a Python tool where we can do an online diagnostics with the available data, I mean, that's a huge advantage. There are other efforts in NASA and in US in some universities, but yeah, for now we stick with DSL Python and we see how it moves. But yeah, as I said, we are learning. It's quite crazy the last 4 years or 5 years now. But we hope that we demonstrate a nice concept to the community. Yeah.
Thank you.
Thank you, Praveen. And Praveen is going to stay here also during the day, so grab him for...
Yeah, there's one more question, if you want to take it.
If it's a quick question, very quick. Otherwise, the bell goes.
Yeah.
Slowing things down. So are you going to try and optimize directly in CUDA, or are you going to take a kind of NumPy route in via like JAX or something?
We are doing it in CUDA.
Directly in CUDA.
Yeah,
Wow.
yeah. So we also, well, we also have NumPy, but we usually use it for debugging and so on.
Okay.
Yeah, but we use CUDA, and yeah, it's working, but it's slow. As you said, it's very slow. But in terms of gain, how much we gain with a lot of effort, we gain a lot of speed with CUDA. Yeah. But it's just that it's expensive. Not everybody can afford it.
Thanks.
Thank you. Thank you. Quick question, quick answer. Thank you very much. So we are going to move to the next presentation. Maheswar Pradhan here from IITM. So Maheswar, you have 15 minutes. I'll give you a 3-minute warning. Thank you.
Hello everyone. I'm Maheshwar Pradhan, working at a Monsoon Mission Group of IITM. So this work is towards resolving some of the long existing challenges using coupled model as a prediction or forecast tool. And this is by better representing diurnal warming and its feedback to cloud and convection patterns. So just to introduce what are the processes that is related to surface ocean diurnal variability. One is diurnal warming. During the daytime, the surface of ocean, that is the skin of the ocean, receives most of the shortwave radiation. shortwave radiation. And in this condition, the surface of the ocean is much warmer than the bulk ocean temperature, which is situated 5-meter or 10-meter depth. On the other hand, during the night time, in absence of shortwave radiation, much of the radiation goes out of the ocean. And in this condition, the surface of ocean is cooler than the bulk ocean temperature. And there are several factors that affects diurnal warming, such as the seasonality in solar insolation, wind and current of the ocean, and cloud cover. But diurnal cooling is almost every time present. I will show that in a while. So in this picture, you can see the time series of warm layer temperature in the red dotted lines, and cool skin temperature in the solid blue lines. What you can see that in some occasions, the warm layer temperature correction can go up to 2.5 to 3 degrees centigrade, whereas cool skin temperature correction stays at around 0.2 to 0.3 degrees centigrade almost every time. And if we compare the bulk ocean temperature against the corrected temperature, we can see that the bulk ocean temperature misses out the high frequency variability that is existing in the surface ocean. And we can get skin temperature from the bulk ocean temperature by including warm layer as well as the cool skin temperature corrections. So these are simple processes, but how does our models represent the surface diurnal variability? We can see that the orange line represents the local solar cycle of sea surface temperature over Bay of Bengal, and the blue line is the model simulation, that is in CFS-V2. What we can see that in observation, the local minimum occurs around 8 hours, and the local maximum occurs around 15 to 16 hours. But in the model, both the minimum as well as the maximum is delayed by 2 to 4 hours, and the maximum occurs in the early evening around 18 to 19 hours. Even if we calculate the amplitude of diurnal variability by computing the maximum minus minimum during a 24-hour cycle, what we can see that in the observation here, the amplitude goes up to the amplitude goes up to 0.6 to 0.7 degrees centigrade over the summer hemisphere. But in the model simulation, the amplitude of diurnal variability is hugely underestimated, and it is restricted to hardly 0.2 to 0.3 degrees centigrade. So even if the coupled models are complex, but simple surface diurnal variabilities are not well represented in model. So I would say that diurnal variabilities of the surface ocean are well studied, well understood, even well parameterized, but they are not well represented. So next, why do we need to improve the air-sea interaction or the surface boundary condition? One reason is to there are several challenges in the coupled model. For example, the previous talk has shown that the phase as well as the amplitude of diurnal variability of precipitation, as if we compare the model simulation against the TRMM data, we can see that in most of the model simulation, it is earlier than observation in most of the tropical regions, and the diurnal amplitude it is hugely underestimated in the model. And there are several studies which try to address this problem by revising, for example, revising the convective triggering function. They could improve the diurnal phase of the precipitation, but there is the improvement in diurnal amplitude was not that significant. And there are other studies which also tried by revising cloud parameterization scheme, convective parameterization schemes to address this problem. On the other hand, we have another view where observational studies have proposed that diurnal air-sea interaction is more important for organized growth of organized convection, and that is through SST and surface fluxes. So we have conducted 2 sensitivity experiments. One in the default version of the CFS-V2, the bulk ocean temperature acts as a boundary condition for the atmospheric model, and the NCAR bulk fluxes that is computed which acts as a boundary condition for the ocean model. In the sensitivity run, we implemented a diurnal skin temperature parameterization, and that acts as a boundary condition for the atmospheric model. And the fluxes also, we have changed the scheme to Quad 3.0, and these fluxes drive the ocean model. So how does it improve the diurnal cycle of the ocean sea surface temperature? For example, here, if you see the control simulation are the dashed lines, the dotted lines is the sensitivity run. As I discussed, the control run, the diurnal maximum as well as the minimum is delayed. But if you see in the sensitivity run, it coincides with the observed diurnal variability, as well as if we see the diurnal amplitude of sea surface temperature. If we compare the sensitivity run against the control run, there is a significant improvement in the diurnal amplitude as well of the surface ocean temperature. So secondly, how does the feedback improves that connects the diurnal warming to the atmosphere? So here we defined strong diurnal warming events and weak diurnal warming events by setting a threshold of plus or minus 1 standard deviation. And during strong diurnal warming, which is in the left panel, you can see the observed observation or reanalysis products. And here, this is a composite of 10-meter wind speed. The winds are very calm over most of the tropical region except the monsoon southwesterlies. And in the control simulation, these winds are overestimated over the North Pacific region and most of the tropical region. But in the sensitivity run, this representation is quite in agreement with the reanalysis products, and the overestimation is usually reduced. On the other hand, during the weak diurnal warming cases, both the model simulation are satisfactorily reproducing the patterns over the tropical Indo-Pacific region. Then moving on to the surface fluxes, for example, latent heat flux. Here also, if we see during the strong diurnal warming cases, which should be like reduced latent heat fluxes, but the control simulation hugely overestimated the latent heat fluxes. But the sensitivity run reduces the overestimation during strong diurnal warming cases. During weak diurnal warming cases, both the model overestimate the latent heat fluxes, which is also reflected in the seasonal pattern, which I'm not going to show here. Finally, going on to the precipitation, how the composite look like. During strong diurnal warming cases where the cloud covers will be less, precipitation is quite less. And if you can see the control simulation over Northwest Pacific and Western Pacific warm pool region, the precipitation is overestimated. And in sensitivity run, the composite looks quite in agreement with the observation. And during weak diurnal warming cases, both the model quite satisfactorily reproduced. But here also, if we can see, the control simulation underestimated the observed simulated rainfall patterns. But sensitivity run, it is enhanced as compared to the control simulation. Sorry about the font organization. So this is the feedback loop that relates the diurnal warming to the the convection. We have done a detailed analysis in this paper, and what we have found that through moisture or moisture convergence feedbacks, the diurnal warming can destabilize the atmosphere and create a stronger active cycle. And that those kind of conclusions are also drawn from like Villager et al., where they've stated that the destabilization of atmosphere can be done through diurnal warming and related surface fluxes feedbacks. So moving on to how these diurnal warming patterns can relate to cloud processes, Johnson et al. Have shown that during strong diurnal warming cases in this period, if you can see, the high clouds or cumulonimbus clouds are reduced, whereas the mid cloud and the shallow clouds are enhanced during this period. So they propose that during the diurnal warming days, they trigger shallow convection, which gradually moisten and they gradually lead to high cloud or high convection during the active phase. Similar analysis, composite analysis we have also carried out, and during strong diurnal warming, high cloud fraction, and during weak diurnal warming, high cloud fraction, where we can see that during weak diurnal warming, which represents basically the active phase of convection, we can see that high cloud fractions are increased. On the other hand, if we see that during strong diurnal warming cases, the low cloud fractions are quite significantly more than during weak diurnal warming cases. That leads to the verification of the hypothesis that strong diurnal warming triggers shallow convection with increased low clouds, and these clouds gradually moisten the lower atmosphere, creating a favorable condition for active phase of monsoon. But if we look at the control simulation, both the strong diurnal warming cases and weak diurnal warming cases, the high cloud fraction as well as the low cloud fraction look similar, and there is no quite significant difference. And if we go to sensitivity run, here we can see that clearly the high cloud fractions are significantly enhanced in the during the weak diurnal warming cases. But again, the low cloud fraction, as it is just opposite to the observation, which would have been like during strong diurnal warming cases, we should have more low cloud fraction, but here it is less. So therefore, the current configuration of the model with by including even the skin temperature parameterization, the shallow cloud or the low clouds are not quite well represented. So this is my final slide. So how does it impact the rainfall, diurnal amplitude of rainfall, where we have stated that this is our problem, which I'm going to address. So here we can see that diurnal range of precipitation in the observation is quite high throughout the Eastern Indian Ocean, Western Pacific warm pool, and the tropic equatorial Pacific region. But in the control simulation, it is usually underestimated, and in sensitivity run, it is amplified because of the earlier mentioned feedbacks. And if we do analysis on convective rainfall over central India also, it is, you can see that it is quite amplified, as well as it solves some of the other existing problems such as drizzling bias or the low rainfall predominance in the model that is being also resolved. So to summarize, these are so we through extensive analysis, we have verified that the diurnal skin temperature and fluxes can rectify into intra-seasonal as well as seasonal scale, and they minimize the biases involved in coupled model simulation. There are still challenges involved in simulation of low clouds, and these are the kind of areas where this development work can fit into. And for example, reanalysis product or data simulation product like ECMWF has already started. So, and short range to sub-seasonal forecast also, like MESO and MGO forecast, and seasonal forecast, we have already demonstrated it. So that will be all from my side. Thank you.
Thank you very much, Maheshwar. We have time for a couple of questions. Here.
Very good presentation. Really impressive result. Just one technical question. So what is the coupling frequency on diurnal?
So current configuration is 10 minutes at what the meteorological parameters are being exchanged, but the fluxes in the default version of the model that were exchanged in 3 hours, hourly or 3 hourly, that we can set.
Okay.
So yes.
So this diurnal coupling happens fluxes 3 hourly.
So that again, because I have modified the scheme now, because meteorological parameters are also being changed at 10 minutes. So in the sensitivity run, the actual coupling is happening at 10 minutes.
Okay.
Even the fluxes.
Okay.
Yes.
So it's a very high frequency coupling.
Yes.
Okay. Thank you.
Thank you. And Yuhei now, just behind you.
Thank you for nice talk. What scheme did you use for these simulations? I mean, the warm skin layer.
So this is Farrell 1996, that is Square 3.0 algorithm.
I see.
Yes.
Okay. I thought that probably the excess response of the excess response of the latent heat flux to the SST data variability may be due to the excess data warming in the moderate weak data warming cases. So let's talk offline later.
Yeah, so at intra-seasonal scale, at least we have verified, we have quantified what is the response of latent heat flux to SST and SST to rainfall. So in model, actually, it was the feedback was underestimated. The response of SST to the fluxes was quite low. So that have changed actually. That has amplified, but still it is not up to the mark of observation.
And one final, thank you. And one final very quick question there.
Thank you, sir, for the nice talk. So my question is, can this technique help to correct the common early biases in rainfall timing that are seen in most models?
So for phase, we have that also we have analyzed for Bay of Bengal phase of rainfall. That is not being that is similar to the control simulation, but over land that is northwest Indian region. The like in control simulation, the rainfall was quite early in the it was in the morning. That is being resolved, and that is being corrected to the afternoon rainfall, which is actually observed.
Thank you.
Thank you very much. Unfortunately, Julius could not join us, so this the session, and I would like to invite everyone for a round of applause again, thanking all the speakers of this session. Thank you very much. And I think we come back here we start the next session at 11:30 sharp. So please, you have your tea and coffee break, and then you come back to start here at 11:30.
Excuse me, please be seated for 1 minute. I have few announcements to make. Firstly, before we go for break, I would request Dr. Dev Nyogi, as a token of thanks, please hand over the memento to Dr. Nico for his valuable contribution and chairing this session. The session timing for tomorrow morning has been moved up by 10 minutes. So I would kindly request to gather tomorrow morning at 8:50 a.m. Indian Standard Time. And we will continue the session, this same session, after the tea break at 11:30 a.m. And tea is arranged at the basement and IITM guest house. Thank you.
ते प्रफुल्ल थोडं लक्ष देऊन हे केलं.
ये चलता है हाँ ये भी ऑन रहेगा नहीं नहीं आगे
Okay. Yeah. Yeah. Okay. That's fine. So we have 5.
Just 1 or 2 minutes, then we will start so that people will.
Yeah. I'll take your cue from you. Okay.
Welcome back after the coffee break. We will continue with our scientific session on simulation and prediction of monsoons, including extremes. To start with our session, I would like to welcome Dr. Marlene Mittenmeyer from Met Office UK.
Dr. Marion works with the model evaluation team with the global model evaluation and development section at Met Office UK. We are fortunate to have you, Dr. Marion, lead this session.
Right. I'm not used to so much introduction. It's very nice. So welcome back. And I've got to do this first. I've wanted to do that since Monday. Anyway, right. So, but I'm going to enjoy using it while I'm chairing. So for those speaking in this session, you might hear it if you go too long. Anyway, right. First up this in this session is, I'm going to try and get this name right. I've been coached earlier on. Partha Sarti Mukotsai. Anyway, sorry, Partha. Over to you. You have 13 minutes, and then I might make a bit of noise with a bell.
Okay. Yeah. Audible? Okay. I'll set my stopwatch before you ring. Okay. I set it at 18 minutes. What is that? 20 minutes. No, I set my stopwatch at 18 minutes. Okay. Yeah. Thank you. Thank you, Chair. Start. Yeah. Okay. Yeah. Thank you. So I have to give a lot of thanks, that on the top, I actually represent WWRP TMR as a member. I thank Dr. Nico. And WCRP, I thank Dr. Indumati. Then IMPO, Dr. Rajgopal, Dr. Ravichandran, Dr. Krishnan, Dr. Mahapatra. I serve Berhampur where I'm working. So thanks for giving me this opportunity to share my results and some of my views, etc. And big thanks to all my colleagues and collaborators, talented, dedicated, who actually make this IITM global high resolution forecast model a reality. Okay, but believe me, I did not tell GMD to publish it yesterday because I have a talk today. Okay, it just happened. Okay, yeah. So anyway, so this model is online now. I mean, this paper is online, freely downloadable. The model also is free to everyone, and I believe people should now start jumping from a swimming pool to ocean, from regional model to a global model, and try, experimenting with the global models. Is it working properly? Okay, so next slide. So this is the paper that has come yesterday, and to me it's a milestone because we so far we are very good in adopting models. We never dare to develop models. This is possibly kind of first attempt, a small attempt, but possibly it will go a long way because there are huge youngsters sitting here, and the good thing is the model is freely accessible, so community can contribute in this model. No one has to take any permission. It is just you go to GMD site and it's everyone's model. And first of its kind, of course, from India. And I gave this photograph because I'm looking odd. They're sitting with shirts. I'm sitting with pullover, But this is in 2018. It's very informal. This very informal meeting. There was no formal MOU. There was no formal, sponsored projects or anything. We just discussed. I was just exploring whether it is possible. Can we do it? We did not have this confidence of making a global model of 6-kilometer resolution. But anyway, it happened. So, it does, yeah. So this is the outline quickly. And okay, I always start with this picture. Whether we go to artificial intelligence, GPU or whatever, I can't forget this picture. By outstanding people. Okay, right from von Neumann to Charney. And this actually, I request all the students to read this paper. Okay, Peter Lynch, 2008 BAMS. Please read it. So they have recreated this 1949 forecast. And what was that? Yeah, so this is the forecast. This is the analysis. This is a verifying analysis, right? So there is a system here that has moved here. What is this? This is the difference, okay? The difference between the, observed change, which is solid, and the forecast change, that is dash. What do you see? That the system has moved here, okay? But in the forecast, it is somewhere here, which is actually, you can see it here. You can say, this is not a very good, forecast. But what Peter actually said, that it is actually a very good forecast in 1949. N7 cardinalis, although the color is not very good, N7 cardinalis helps show that 4 historic forecasts made in 1950 with the pioneering electronic computer all had some predictive skill. It's very important. 1949, amazing. Okay. Now I will show another figure. This is much later. In 2009, paper published. So one of my students and Dr. Sanjay, so we were doing a very simple analysis. Okay. What we were doing, so this analysis, this is GFS forecast in 2006. This was a time when monsoon onset was happening, okay? And this is a 200 hectopascal divergence. What it shows the divergence is moving northward. It's natural. Why? Because the lower level convergence is moving northward, right? That's how the monsoon manifests. But when we come to the forecast, it doesn't move, okay? So this actually shows, now if you compare this forecast with the 1949, you will surely agree, oh, wow, this is really good, okay? This was the situation in 2000. And we also, by the way, started in from this. This was our initial, status in 2006, not very far from today. So what we said here is that poor representation of vertical advection of zonal wind in the middle atmosphere leads to misrepresentation of convective processes. So we were getting puzzled with these convective processes since 2006. Okay, so now we are hearing from day one that there are multi-scale, there are convections and so on and so forth. I will request that whenever you mention about mesoscale, okay, please refer this paper. of which Moncrief and Duane-Walliser, again published in BAMS in 2012 as a part of YOTC, Year of Tropical Convection. Okay, so there in this beautiful paper, he very nicely mentioned that high resolution global numerical prediction model may crudely represent large MCS superclusters, but MCS and other mesoscale dynamical systems are absent from the traditional climate model. Organized convection is not parameterized. And this is valid till today. Why? Okay, this is older slides. WCRP grand challenge on cloud and circulation. They also kind of echoed the same thing, tackle the parameterization problem through a better understanding of the interaction between cloud and convective process and circulation system. And why it is not moving? Yeah, sorry. Okay, so yeah, and this is the this is again by WCRP that this is the feedback, water vapor and atmospheric dynamics, which they said is not very good. Okay, so what is the conventional paradigm? So this slide again I showed to many places, and I will keep on showing these slides in many times. Let me go to the next slide. Okay, yeah, so this is I think a much more easily understandable slide where Arakawa in 1974 gave this hypothesis that the moist convective process, that is a cloud, and the large scale, they are in balance. Okay, so large scale influence the moist convective process. Moist convective process consumes the the moisture, the cape, and etc., and gives back to large scale process, and they are in equilibrium. He said they are in equilibrium. In a much more detailed way, you can get it here. The large scale process destabilize, moisture destabilize the atmosphere. So moist convective instability gets consumed by cloud. It will produce kinetic energy, right? And then that produces warming and drying, right? That goes as a feedback to large scale model or environment, okay? Photo level. Thank you. Okay. He will put it in the website. Anyway, so now if you read this paper by Patak et al. In 2019, okay, a student of IIT, you will see that he has said that all convective closures, unfortunately, they're all cape. Okay, so all CMIP 5 and CMIP 6, they are somewhere or other following what you just showed in earlier slide. Oh, sorry. So now, what we did actually in one of the paper, Professor Zhang already showed by observations that this quasi-equilibrium doesn't hold good in tropics. Okay, and we showed it from model that it doesn't hold good in the model either. Now here you see this is TD 126, 382. Mind it, this error bar, I mean this color bar is not same as that. Okay, so this blue color is 70, this is something like 40, this is 500, this is 200. So actually, the error 5, if we assume this as a reality, this is telling no, nature, we are not in equilibrium. But model is telling no, we are in equilibrium because model is abiding Arakawa and Schubert. Okay, model is faithfully abiding by quasi-equilibrium. So the values are less, the values are more. Okay, so this is a starting point. Okay, so this is one results from Mollai's paper. Okay, you can see many discussion on diurnal. You can see the model keeps on raining, the same type of rain throughout the day, whereas observation doesn't show that. This is a scatter plot between OLR and rain rate. These are observations, and this is 2 model. Yeah, now here, this is from another paper in GRL. You see, we just computed the transition probability in Markov chain, concept. This is from GPCP. So P00 means the probability from no rain to no rain. 0 to 1 means no rain to rain. 1 means rain to rain. 1 to 0 means rain to no rain. Okay. Now, if you keep everything aside, just concentrate on this rain to rain. Okay. This is observation is telling. Look at these two models, low resolution, high resolution. Extremely overestimated. So what does it mean physically? It means that model is trying to remain in the rainy state. Okay, model is preferring once it goes to the rainy state, it skips raining, okay? And as a result, this is the manifestations, okay? This is a recent paper by Walk et al. In JGR. So you get CMIP 3, you get CMIP 5, you get CMIP 6, okay? Everywhere you see a similar error, a similar bias, okay? Because it has this tendency, okay? Now, yeah, this is an old paper. I was just wondering, even in regional model, that's CMIP model, regional model, this is in weather forecasting 210. We made a regional climate, 10-year, 7-year, 10-year run. And you see, this is the observations where you can see these epochs, right? So rain, then there's a break, then there's rain. But you see, there are 3 different convective parameters in BMJ, Betz-Miller, Janich, Ken, Fries, or Grail. It keeps on raining, okay? So they prefer to remain in, the probability of rain to rain, okay? But then I was wondering, so we were completing almost 50 years of Arakawa-Schubert's in 2024, and no one is challenging, right? So I was very happy. At the fag end of 2024, it came, I think, in December. Okay, a group of GFDL people, including our friend Leo Donner, they said that no, you consider non-equilibrium. You have to consider non-equilibrium. Okay, if you consider non-equilibrium, many good things will happen in the model. What is that non-equilibrium? This has problem. Yeah. So this is the non-equilibrium. So the rate of change of K is not just influenced by the large scale, what Arakawa suggested, but by what? By boundary layer, by free troposphere, by deep, by shallow. You can add many more if you have observations. Okay. So the trick is that if you can contribute, if you can include the contributions from these non-equilibrium component, okay, you will definitely get a better performance by convection. Okay. One example, Western Ghat. No model includes it. Western Ghat topographic ascent is a mesoscale. Model doesn't do explicitly. Okay. So this is the key. Okay. So I'm very happy that in GFDL at least one paper came, no AI. Okay. And they have what they showed is very impressive. Okay. Look at this. So Asia. Okay. They are able to push the diagonal peak towards the reality. This is good. Okay. Okay. And our CFS, if you see the diagonal PDFs, they look like hockey sticks. Okay. And if you do some kind of tweaking in the model, it definitely looks better. But still, it doesn't capture the mesoscale. Okay. So yeah. So now coming to extremes. Okay. I have around 5 minutes. So in extremes, these are the lone papers we all know. Everything is increasing, rainfall beyond 15 centimeters increasing. Roxy said that all over central India, the floods are 3 times. We have heard also. So this is the scenario. Now there is a recent paper, very recent paper in 2025. I think this is the first time someone has attempted a, trained in sub-daily scale rainfall extreme. It was not, nobody has done it. They have done a huge, some student from IISER Tirupati. Excellent paper. I'll request everyone to read it. Okay. And see, they have made a very important statement. Frequency of short durations HRE, high rainfall events, over central India and long duration HREs over northwest coast of India is increased in the recent decades than in earlier decades. Very important statement from real data, not satellite. Okay. And CMIP 6 historical blah, 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 are not able to simulate. We know that. We know that. It cannot, right? So we are. So this is the trend they have showed. And this is one example because I'm in Berhampur. So it took, in 2023, this is what is happening. Short duration, heavy rainfall events. Okay. People even don't know that by evening, we are going to get 18 centimeter rain. Okay. And the city is getting flooded. Okay. So, and this is a recent book, okay, Multi-Scale Precipitation Variability by Shige-san and many others. There is a chapter, please read it. Shige-san, Makur, and Hirose-san has written very nicely. And what they have said is very interesting, that this is what you see is the rainfall that is falling between 10 to 100 kilometer size. Okay, this is actually falling in mesoscale. So there is a huge contribution from this, mesoscale, which all these models are missing. unfortunately. So coming back, somebody was mentioning about Kerala. This is a well-known figure from our weather forecasting paper. And you can see all the black lines are observations and all other lines are from model. I can see except this green line, no one is coming closer to observations, and that is only day one lead, only 24-hour forecast, right? So the model is not doing good job. If you consider ensemble, if you consider probability, it is doing slightly better. So yeah, now you see this is AIML, okay? Forecast, thanks to Manmeet and Siddharth. So this is a forecast-net model, this is a GraphCast model. So you see, this is somewhat looking like GFS, right? It's not getting those mesoscale hotspots in the embedded in this Kerala rainfall, okay? So everything is not quiet on the western front, okay? So the point is, so what are the to-do list for extreme? To-do list is locations, time, and intensity. And how do we go? Oh, okay, so this is another paper where we just wanted to see whether is it okay in GFS operational, the cloud and rainfall. We found that no, things are not okay. Okay, this is a recent paper. Okay, okay. Now, so based on this, we just developed. The whole effort has gone into this. We started from held sewerage, only dynamical core, then aquaplanet, then adding the orography, adding the vegetation, and getting the finally 3D model. Okay. Now this model is showing, this is a plot of relative humidity. Okay. This is the log of rainfall, and this pressure. Okay. What we wanted to see is that the boundary layer is normally dry, is very dry. Okay. So whether that dryness of boundary layer is improving, we find yes, it is improving. Okay. That is one of, and that is one of the systematic bias in any semi-5, semi-6 or CFS model. Okay, the boundary layer problem. And this is just to show that if you just make a model, non-hydrostatic things doesn't go handy. You see, this is a recent paper in discussion right now by Bjorn and other next generations kilometer scale model. And you see, this is IFS. Okay, age old. I mean, this is a completely double ITCC structure. Okay, and in this model there is no convections. Okay, and in this model convection is there. Okay, so you can, I mean, we cannot just say that just switch off convection, everything will be fine. Switch on convection, everything. So it's not so easy. It's not linear. Now this is the same plot we made from I merge GFS, the TCO. It looks fairly good. Okay, at least not that awkward. And this is the this thing. I will finish in a minute. This is the wave number frequency. I found this as well. Yes. What? 2 minutes? 1 minute? 1. Yeah. So yeah, we could see that even this the heavier rainfalls are also predicted well in 2022. It is 2023. So what we find is that the moderate rainfall reduces and heavy rainfall, it is improved in the longer lead. This is another example, okay, of good rain. Now this is last 2 slides. So please read these 2 papers, okay? Intensification of daily tropical precipitation extreme from more organized convections. And another by Tompkins and Sevi 2017 in GEMS. In these 2 papers, okay, they have actually defined from model how we can define organized convection. Okay, we qualitatively tell organized convection is like this, it should look like that, but they have given an index. Okay, I cannot go into the technical detail of that, unfortunately for the time, but we use that in our model, and what we find is that it's not very good. I don't like this slide, but you can see that what we find is that if the index is 0, it means it is random organization. If the index is greater than 0, it is clustered organizations. Okay, and if it's less than 0, it's kind of popcorn type of organization. So we find that in many heavy rainfall events that this TCO is trying to give a better organizations. Okay, concluding remarks. But my conclusion is not just slides what I showed. So please read it. Kilometer scale model has come. Okay, that's good. The model shows promise in capturing many things. Initial results suggest that the model captures organized convection relatively better. But now, this is important. Okay, more research and improvement needed. Incorporate non-equilibrium closure, please. All the students, please break your head to bring non-equilibrium closure. Incorporate mesoscale closure. And to do that, read this paper. They have said very clearly, total column water vapor, mid-level humidity, and vertical moisture flux. These three things has to work well if you want, mesoscale close things to develop. Other than that, shallow and deep explicit approach, AIML, now I bring AIML-based convective trigger, AIML-based microphysics and radiation, and ML-based post-processing. Stop here. Thank you. Any question?
Thank you very much, Pater. One question. Anybody got a burning question? Either online or here in the auditorium. Very nice overview. There's a lot in there.
Yes, that's it. Where?
Nice talk, sir. Thank you.
Thank you.
I'm interested in knowing, do these improvements mean anything for future projections, like longer time scales, like decadal and beyond?
So we have not run the model.
Yeah, but
for such a long.
just generally, like when we are developing models, like
Yes. So I can tell you from our experience in CCCR, what we have seen that if you improve something in convection, that of course improves your climate projection as well. Okay. So because the convection and cloud, that is one of the ingredients that, like is there, whether you go to decades or you go to multi-decades or you go to centuries. Of course. Yeah.
Thank you.
Thank
Please
you, Chair.
ask Pater some more questions if you have them afterwards. Thank
Yeah,
you very
I'm
much,
here
Pater.
till last of this.
Sorry, I made a mess of your name. Anyway,
No
then
problem. Everybody does that.
let's thank Pater for his talk. Okay. At least for the next two talks, I think I can manage the names. The next up is John P. George, and he's going to tell us about some more NWP experiences at NCM IWF. Yeah. You have a memento that I'll have to give you. Right. Where is John? I'm doing well, folks. Anyway, right. John, you have 18 minutes before I ring a bell. Okay.
Good afternoon and good morning. I will be presenting the work of many people who contributed to the development of NCM NWP system. So basically over the years, whatever our effort on improving the model, how it is reflected in the improving the forecast, especially the forecast of monsoon. We are engaged in the high resolution for using the high resolution model for the short range NWP, the medium range forecast systems, the global forecast system, and the coupled forecast system for the S2S forecast, the data simulation for ocean, atmosphere, land, land surface, and the sea ice. And then the two reanalysis we could produce. So these are the major engagements, our engagements, and our mission is to continuously develop and advance the NWP systems. So our journey started in 1988, and And from 1994 onwards, we are operational center producing the operational NWP. Initially, we were producing only the medium range forecast. This is the, we were started using the IITL18 system, what's a 150 kilometer resolution model. And now currently we are using a 12 kilometer NW and the global NWP system for the medium range forecast. So that is the progress. And over this progress in the last 25 years, what is the skill we could achieve? This is against Indian radio sound observations of Day3 wind validation at 850 hectopascal over the Indian region. You could see how our RMSEs are reduced. But still in the monsoon, the RMSEs are each year, if you see it, the monsoon RMSEs are the maximum. So of course that is also reduced, but still it is very, very high compared to the winter season. So what all I will go through in my this presentation, I will go through the improvements of model resolution. What are the various improvements we could do, and the use of the coupled systems. Operationally, we are in S2S forecast. We are using the coupled system, which is actually in a couple of months' times. Even in a medium range forecast, we will be using a coupled system, and the better representation of the physical process. See what are the changes we made, and the data simulation improvements. And I'll focus on some of the verification results, and which is the verification results we are exchanging with the WMO lead center, both the deterministic and the ensemble. So all these achievements are possible through collaborations and the in-house R&D. And in the initial years in international collaborations, we were in with NSUP. We were collaborating largely with NSUP, and later on period, we are largely collaborating with the Met Office through different programs, including the core partner of the Momentum Partnership and the WCSSB program. So we get all the observations, and we received all observations from various sources. Not able to identify where is the window. Stop. Thank you. Sorry. This we receive the observation from various channels, continuously receiving the observations, and that is processed and quality controlled and used in our systems. Not only the atmospheric observations, all the ocean and land surface observations are also processed at NCMRWF. And over the years, you can see that there is a large increase in the observation volume, and we routinely we compare it with the different other global centers also. This is a comparison with the ECNWF, and see that our volumes are comparable with other national global centers. And over the years, our data simulation systems, there is a big progress in the data simulation. We started with an optimal interpretations scheme, and now we are a hybrid 4D-VAR for our UM-based system, NCUM. We call it NCUM for the global medium range forecast system. And then there's a hybrid 4D and VAR analysis we use it for preparing the GFS analysis. So both are run at NCMRWF. So these are the progress achieved over the years. So, and we try to incorporate all make use of the all Indian satellite observations. These observations are now operationally going Oceansat 3, INSAT 3D. So some of the observations are operationally assimilated now currently. Some are used earlier, like megatropics, which impact was very high. And we continuously monitor the impact of the observations also in the forecast. And accordingly, if some of the observations we we take if it is not very good, then we will decide based on the quality of the observations. So see, continuously monitor the observations and its impact of the observations on the forecast system. So these are the in recent times, these are the major publications which before introducing any observations, we do the different data assimilation diagnostics like OSC or observing system experiment or the forecast sensitivity to observation. Those type of diagnostics we do, data assimilation diagnostics we do, and the see that what is the impact of the each observation, each type of observation on the data assimilation system and the forecast system. So these are we are continuously monitor the impact of, this is a monsoon time, how each type of observation performed over the years. Of course, to 24, I by mistake, I could not add it. So it was every year we monitor, every day we monitor it. What is the impact of each type of observation, each point, what is the impact of the observation on the forecast, 24-hour forecast. And as I already mentioned that we have improved resolution from a 150 kilometer to a current 12 kilometer in our global medium range forecast system. So in 2018, we improved to 12 kilometer. Now we have another 6 kilometer development is there. This is an experimental system, and it is a 6 kilometer atmospheric model. So I'll show some of the results from the 6 kilometer model. So these progress in our resolution, you can see that this is a last monsoon, July 30th, July 24. There's a heavy rainfall occurrence in over Kerala, and which was the big landslide, and many casualties happened due to that rainfall event. That is, you can see that up till day 3, it is this is day 3, day 4, day 5. Some shift in these titles. Sorry for that one. So actually you can see that this rainfall episode is captured up to day 3 nicely in the system. Of course, some signature even up to day 5 we can see it. So this is the observations. So the higher resolution models, this is a global model forecast. So in the global model forecast of 12 kilometer resolution, you could capture these events reasonably accurately. So that is a big achievement. That is mainly comes from the resolution advantage. Of course, the physics and data assimilation and all those things will be contributed to these developments. So we are actually continuously see that different physics packages, how it is impact of the different packages, physics packages on our forecast system, whether it is improving, what is the improvement, how much we are trying to quantify the improvements. These are the different packages, global atmosphere and land, different packages are there. So we are trying to see that how much, whether if we going to the GL8, whether it will be improving our forecast system. This is Kormov and the convection schemes. So various schemes we are continuously testing. I'm not going to the details of this one. And we are developing also some of the schemes. Other one is a metaphase combinations. And we are also developing our own this lightning scheme. We have made modifications and we have developed some blended schemes. And we saw that it is improving the lightning forecast over Indian regions. So through collaborations and through in-house developments, many things are, many improvements are happening into our NWP systems, not only in the global. I'm just focusing on the global NWP system, which is used for the medium range, but we have the very high resolution 330 meter city scale model is there. Many changes are made into that one. So there is a urban features are added to that model, and it is tuned to the Delhi city. So many development, and it is a nearby areas, whatever the irrigation. So those things are also added. So many developments are happening to our modeling systems, which is contributing to the improvement of the forecast, especially the monsoon forecast. Another development is the coupled coupled model. Initially, we started using the coupled model for the sub-seasonal to seasonal forecasting, this portion. So now we are testing a two coupled systems. One is a global coupled system for the medium range forecast. This is a 10 kilometer atmosphere and 25 kilometer ocean. And there is a very high resolution regional coupled system that is a 4 kilometer atmosphere and 2.2 kilometer. Both are based on the Metrovis system. Of course, we try to improve the analysis of the system by introducing the assimilation of the satellite derived salinity. So these are the biases of the these coupled system we run for the last two monsoon seasons, and we see that what are the benefits, whether any benefit we are gaining from the running the coupled system. Is difficult to see this one. I'll go through this scorecard. Can see that in general, whether it is in a probability of detection or a false alarm ratio or ETS or bias, in general, it is that the higher lead times, maybe after 1 or 2 days, the coupled system is giving a better prediction skill. So not only even in this is an event which has happened in the 2023 in the Himachal. There is a big rainfall and associated flood happen. So that also you can see that in our coupled system, you can see the signature in our operation system. Even the day 5 forecast that it is not very well captured, whereas in the coupled system it is captured very nicely. So this type of signature, even the higher lead time forecast, we are seeing even in a mesoscale systems also we can see some improvements. And the other one I already mentioned, that is 6 kilometer model development. So we have developed a 6 kilometer model, and that based on again a UM system, but it's the many development that happened in our system, our NCM RWF, and we made it to a 6 kilometer model. And we could see that even in atmospheric kinetic energy spectra, see this portion, we can see that the slope is comparatively matching with the whatever the ideal slope, which is that means the representation of the mesoscale features are better in the 6 kilometer model in the global system. So 6 kilometer global system is able to represent the mesoscale features in a better way. So this is a parameterized, of course, 6 kilometer is a gray area, gray convection. So gray area. So we are actually both the parameterized convection and the explicit representation. We are seeing it that in the explicit representation, it is again better than the parameterized convection. So these are in the sub-seasonal to seasonal forecast system. Again, it's an ensemble based system, and there also we can see that we issue the forecast, we produce the forecast, not issue forecast, and we can see that even day 1 forecast is very good. These are the operational forecasts, and in some of the scenarios, even in a day up to week 4, the forecasts are very good. So here it is not that good, but many occasions it is even up to day 3, week 3, week 4, the forecasts are very good. This is the weekly forecast for 1 month, and this is a seasonal forecast which every day, every 23rd of the month we produce it. Again, it is an ensemble system, and there also we can see some of the months. If you take it's a forecast issued in the May 2024 initial conditions, you can see that the June forecast was very good compared to the observations. But when you come into these are the observations, can see that in July and August, July forecast is not at all good, and August is reasonably okay. So that variations are seen in the the seasonal forecasting. This is the mean for the 3 months. There are benefits you can see, and at the same time, the model forecasts are not very good in many cases. So another thing is our development in our ensemble systems. This is ensemble. I'm not talking about the seasonal ensemble. This is the medium range ensembles. We have a 22-member ensemble system. It is operational in the current operational system is a 12-kilometer, and it was in 2018 it started to a 12-kilometer system, and it was that time it was the highest resolution ensemble prediction system in the world, also in this medium range time scales. So later on, we are not because of the computational limitations, we could not increase the resolution of the system. So, but 1995 onwards, we are experimenting the ensemble systems in the medium range weather. So similarly in the 94 onwards, we are experimenting with many of our high resolution systems. These are the 3 operational systems currently at NCMRWF. This is a 4-kilometer model covering entire Indian region, and there is a 1.5 kilometer and a 330 city scale model. So these are the 3 models currently operational at NCMRWF in the high resolution for the short range forecasting. All these things are contributing to this is a coupled regional model. All these forecasts are contributing to the improvement of our forecast. All these improvements are contributing to our forecast improvements, and we are continuously exchanging our the matrices with the WMO, the lead centers, and the lead center verification, both the deterministic and ensemble. And our ensemble forecasts are available in the TIGI website of the hosted by the from 2018 onwards. Our daily ensemble forecasts are available from the TIGI website hosted at ECNWF. So another 1 minute, Elf. So we have produced 2 reanalysis, one regional reanalysis. This is for the 42 years, and many basic data observation data set is taken from the ECNWF, and we added many of the Indian observations, which is not part of the ECNWF data observational data set. So, and produce a regional reanalysis of 12-kilometer resolution, and this was also very high resolution. I think over this Indian region, this is the highest resolution available, and we have a global reanalysis for 20 years also. So these details of this thing, you can see that the Journal of Climate paper, our climate paper, we can see that details. So it's already many people are using it, and it is a user. You can see the around 5,000 users are there, registered users, and this paper itself have one is 2021 paper is having more than 160 citations, and many people are using this data and doing it for their R&D work in weather and climate studies. So I am stopping this. We are engaged in we are actually making use of this IMDA reanalysis and to train our AML model. So I'm stopping here. Thank you very much. If any.
Thank you, John. Right. I see one hand already. And I don't know who's monitoring questions online, but if you've got something to ask online, please do.
Yeah, thanks for the nice presentation, and thanks for the services. What interested me was this kinetic energy spectra figure that you showed.
Yeah.
So with the same resolution, when you switch off convection and switch on convection, you see a different pattern of this kinetic energy spectra.
Yeah.
And if I'm not wrong, the kinetic energy spectra was maximum to the tails in the switch off the convection simulation. So do you know the reason why such a behavior happens? I'm sorry, I don't remember the slide number, but
Okay. So one thing I can tell you, because I'm not a co-author to that paper, but Dr. Raghu, he's sitting here, he was a co-author to that paper. You can discuss with him details. But what I understood is that that slope is better represented in the explicit model, whereas in the parameterized model, it is slope should be, I think, minus 1.66 or something. So it should be that is the ideal thing. This is 200 hectopascal. So that particular plot with your kinetic energy at 200 hectopascal. So if it is a 1.66, that is the ideal for representation of the mesoscale features in the model. So that is what I understood, and which is better represented in the explicit. So I think the details you can talk to him.
Yeah, I'll talk about the processes responsible. Perhaps it's important.
You should be around.
Yeah, thanks.
All right. Do I see one more hand? I can maybe do Dr. Krishna.
John, thank you very much. That was a fantastic talk. This RMSA of the wind speed.
Yeah, the first one. First one. Okay.
Can you show that? Why it's happening? Can you tell? Is it because of the model improvement, or is it because of the data? What is making it?
Yeah.
That's very
In
impressive.
the first talk today, and not first talk, Dr. Vijay's talk, he was asking, similar question was asking, and he was telling that the resolution is the main contributor to the what you can say improvement. I am not very sure that only resolution is contributing. Of course, resolution will be contributing data. The initial conditions are largely contributing to the improvements. So multiple front, it is actually, it's maybe difficult to isolate and say that we have to do many experiments and see that which one is contributing to the maximum. That I don't have any evidence for that one. So everything together is contributing. But major contributor may be the data in initial condition, because we are seeing that in many occasions, if initial conditions, even our past case also, when you use the ECNWF initial condition, it is better forecasted. So initial condition plays a very, very important role. So that is one thing. Another thing may be the model all together means the resolution plus the parameterization and the representation of all the processes, how good it is. So everything is that together may be playing a role. I may not be able to tell which one is contributing to which percentage.
Thank you, John.
Right. I also have questions, but I'll leave them until later.
Yeah.
So I'll talk to you later, John. Right. So let's thank you for your presentation. And
I would request Dr. Mariam to thank Dr. John Fisher with a memento.
okay, so our next talk is Martin Wiedmann from University of Birmingham in the UK. So he's getting mic'd up. Martin,
Yeah.
13 minutes, okay?
Yeah.
Okay.
Hopefully okay.
All right.
Not too many
Thanks.
slides. So yeah, good morning, good afternoon, everybody. I'm presenting results from one of the WCSSP projects. It's called HEPI, Heavy Precipitation Post-Processing over India. And the first part of the talk will be about phase one, which we did in 2019-20, was about a year's activity. And then I have some updates from sort of phase two for us, which we started a few months ago. I want to acknowledge, as usual, the people who did the real work. So it's all about ensemble model output statistics. It's about post-processing the forecast from the NCMRWF, and all the programming for the classical EMOS has been done by Michael Angus, who was with us now at the Met Office, and all the programming for the new machine learning versions has been done by three people: Chandni Thakur is new with us, Kelvin and Noemi Gonçal. And then I also want to thank Raghu for his wonderful support with the data and everything. And then the usual people who did channel proposal writing and support. Why does this not change? Okay, so just for those who are not familiar with this, what's the basic idea of EMOS? The idea is that every day we have an ensemble from the forecast, and that ensemble is probably not perfect, and we want to give ourselves the freedom to transform that ensemble. So this is an example for temperature. So this may be the old ensemble, and we want to do a new calibrated ensemble where it may be shifted and we may change the variance. It's super simple, yeah? What we're saying is the new ensemble mean may be a linear function of the old ensemble mean. Yeah, so we shift it and we scale it. And the new ensemble variance is also a linear function of the old variance. As simple as it gets, every 12-year-old can write that down. What's not simple is finding those parameters in a way that optimizes the forecast skill. And our optimization criterion is the usual continuous rank probability score. And for the rainfall that we're using, we're not using a Gaussian distribution, we're using a truncated gamma distribution. And these are the results now, which we published last year. That's the mean rainfall, that's the mean bias from, we used 5 years of ensemble forecasts. We used cross-validation. So we always fitted the model with 4 years, tested on independent years, did this 5 times. I'll come back to that panel later. Let's start with this one. This is, so what we're showing here is a continuous rank probability score. So we compare the PDF from the ensemble with the step function PDF that's given by the observation. And this one is a fun one to look at. I thought it might be helpful to check whether the climatological distribution is better or worse than the ensemble forecast. And NCMLWF might be pleased to know, which you knew probably already, that in most areas, the forecast is better than the climatology. However, there are some areas where it's actually not true, which is also interesting. Then another reference method, so climatology is a reference method, right? Another reference method we use is quantile mapping. Yeah, we just look at the empirical quantiles and we say, let's fix it. Interestingly, quantile mapping obviously by construction gets the marginal distributions right. But if you look at the forecast skill in terms of CRPSS, it actually degrades the forecast. So that's, I still haven't fully understood how this is possible, but it's obviously true. And this is the result that we get if we apply ensemble model output statistics in the way I just explained. And we can see that over most parts of India, we get a moderate improvement, and over some areas, we get actually quite a substantial improvement in the CRPS. And the map up there shows now for each location which of the different methods of the raw forecast, the climatology, the quantile mapping, or the EMOS gives us the best CRPS. You can see quantile mapping nowhere in most of the areas, EMOS, and in some areas, the raw forecast was a bit better. And I just discussed with Raghu yesterday, we have now more data, so we can refit it, and there's probably some element of noise here. Next question then is, I mean, it's heavy precipitation forecasting, so it would be good to know that we're making some progress with respect to heavy precipitation. So we also checked the Breyer score with the things still optimized with respect to the CRPS. If you do the same story here for the Breyer score, we see again that the climatological distribution is in many places not helping, that the quantile mapping degrades the forecast, and the EMOS still improves the forecast with respect to the exceedance of the 90% level. The comparison here with which model, which method wins is a bit more scattered, and we'll see whether some of this scattered goes away and it's just noise, or whether there's something substantial about it. So remains to be seen. Then a few more checks, obviously. It's not only about those scores. We picked a few locations here across the country, and we can here see, these are the marginal distributions now for the data, which is the IMD observation data, the raw forecast, the quantile mapping, and the EMOS. And I don't want to go through all of them, but you can see that the black bars, which is the raw forecast, you find a few examples where it's actually, well, substantially different from the observations, and the quantile mapping, unsurprisingly, gets the distribution right. That's what it's designed to do. And the EMOS is usually fairly close as well. So it doesn't do anything horrible, despite the fact that it's not designed to really give you the right distribution. Another aspect of forecast is over-under dispersion, over-under confident. These are rank diagrams. What we want is, so for those who are not maybe familiar with this, so we take the 23 ensemble members and the observation, and we ask, if we rank them, where's the forecast? Yeah, sorry, where are the observations? And if the observations, for instance, like here, are most of the cases in rank 24, so that means they're the driest of the lot, that means the forecast is too wet. And what we want is that the distributions here that were shown are flat. If we have a U-shaped distribution, a bit like here, it means the forecast is overconfident. So the observations are often either too low or too high. What we see, make a long story short, the raw forecasts have some really deviations from the flat curve. Quantile mapping sometimes improves it a little bit, sometimes makes it worse. And in general, the tendency is that the EMOS makes it better. So far, so good. And last but not least, then we go to the machine learning bit. These are the reliability diagrams for the exceedance of the 75th percentile, which stupidly this slide doesn't say. The 90s, we didn't have enough data, so they were too noisy. And what you can see, what we want is that the curves, so the observed fractions relative to the forecasted probabilities should be the same, so they should be on that line. And the blue ones here, the EMOS ones, have a tendency to be closer to the line than the raw ones, and the quantile mapping ones. You can see some that look a bit crazy. That's an indication of we don't have enough data to do this properly. But in general, it increases the reliability. Now, so that was the old project. Then the new phase, the Happy ML, is about saying, well, this is what I just explained. That's the old stuff. How about, I mean, basically the story is everything that's done with statistics somehow these days needs to be tried out with machine learning. So this super simple linear transformation could maybe be replaced with something more complex, some machine learning stuff. It means as input, we can not only use the mean and the standard deviation of the old forecast, we can maybe take the whole distribution or whole spatial fields. We can not only optimize the continuous rank probability score, but we could maybe directly optimize the prior score or any other measure for extreme rainfall, or even user-defined metrics, whatever the user is interested in. And the output can also be non-parametric distributions or full fields. So a lot of wonderful things can be done. This is again in a list. Maybe I should point out one more that I haven't shown before. We could also use additional predictors about the large scale scales or things that you mentioned this morning, the factors that are relevant for affecting rainfall, that can be all included. And of course, at some point, we want to get interpretable AI, apply those concepts. So then we thought nothing easier than reproducing the classical EMOS with throwing a multi-layer perceptron at it, so doing local post-processing. And we spent a few months on it. So structurally similar to EMOS. So if you have only one layer, you can, and do this right, you make a linear regression out of this. We implemented it first with non-parametric. So I should say that the classical EMOS assumes that the output distribution is a gamma distribution. That's an important part of the story. And so it did not work very well at all what we did. Then we thought, oh, maybe because we did not use a parametric distribution, because that's obviously a lot of help if the method doesn't have to figure that out itself. Then we implemented a parametric version. It still didn't work. So my current understanding is, or guess, all to be confirmed, is that the reason is that we don't have enough data. Yeah? Machine learning is great if you have data, but we have 5 years of forecast data. That seems to be not enough. And in the classical EMOS, with this wonderful Broyden, Fletcher, Goldfarb, Shannon algorithm, which is the optimizing thing, that seems to work wonderfully well. So we're going to dig a bit deeper here, why it's not working. Then we, Andrew Robertson showed a talk already using UNet for S2S. We're using this for what we're doing here. I should point out, it comes from image processing in biomedical image. Then Jose Gutierrez group and people working with him had some early papers where they used this for downscaling. In that paper, there's a nice table, and Chandni actually made this figure here out of it. Number of studies, different countries. So over the last few years, that has exploded a little bit in the concept of climate. Climate, downscaling, perfect proc, that sort of stuff. Andrew and we, I hope I'm not doing some injustice to someone. I think we're the first one who trying this for forecast post-processing. What it does is it takes full spatial fields in, then it does convolution. So it tries to extract relevant features, which is black magic, how it does that. Then it has those max pooling layers. So it condenses it, so it forces it to get the essentials out, and then it expands it again. These are the first results. So we've done this now for the last 4 to 6 weeks with Jenny. So this is really early days. So I thought this is not going to work before I show up here at the conference. And interestingly, we got it to work somehow. So somehow means this is not the final product. So what we're doing, we're sticking in the 23 ensemble members from the forecast. And we're just to make sure to learn walking before we run. We output only one field, the deterministic output field. So this is about the most complicated way of producing one field from 23s. The easiest way of producing one field from 23 is ensemble mean. But this is just us learning to walk. I was delighted. These are 3 days, independently estimated, and these are the observations for these days. I was delighted to see that despite all the black magic, the output of the unit is sensible, right? It's not garbage. It's what we see, which may be disappointing, and we need to dig deeper. It's very blurry, which these things are known to be. 2 comments on this. The blurriness can, I'm sure, get reduced if we play with the architecture, you know, how much we compress things. The other thing is, if you look at this and this, you may say, oh, the ensemble mean looks nicer because it has more spatial features, but they don't look like the observations. So maybe this is the more honest answer. Rather no spatial variability than wrong spatial variability. And the next step anyway, again, this is us learning to walk, is the next spatial field we will put out is the standard deviation of the gamma distribution. And then we'll make this into a full probabilistic representation. And then we will do the whole cross-testing, all the things I showed you before. So that's where we stand. Are we getting that? Yeah, perfect. I just killed it. Okay. So long story short, or summary, so the classical EMOS works really well. The machine learning, and we are working on discussing operational implementation, and it mentions here improver, and yesterday afternoon we figured out we may not need improver, so that's great. The machine learning based EMOS does not work very well for reasons that we're going to dig a little bit deeper, lessons to be learned, and the unit seems to work surprisingly well. Of course, we haven't reached the end of the story yet, and we can also use other similar architectures and play with that. So that's what we're going to do the next year or 2. Thank you very much.
Thank you, Martin. Very interesting. I see a hand. Anybody online?
Okay. Yeah, thanks for a very interesting talk. One clarification. What is the lead time here?
Oh, sorry. Yes. Thanks for the question. I looked at my slides and, well, I should have put the slide. No, absolutely. So the lead time at the moment is only 1 day.
Okay.
Just because we had only a year to develop.
Okay.
Of course, we want to do it for lead times of 2 and 3.
Yeah.
Thanks for the question.
Okay, thank you. Yeah, so that's the main difference, I think, from what I presented, which was for sub-seasonal. So it was for weeks 3 and 4. So here's for days. So in terms of the training sample size, then you have a forecast every day, yeah? So what is the training sample size
Well,
over
it's,
your...
I mean,
you
it's
have many more samples than I did because mine are weekly, whereas yours are daily.
Yeah,
probably.
Exactly. We have 4 months. That's broadly speaking 100 days, something of that sort. And we have 4 years to train it. Yeah, so we have 400.
Thank you.
Okay, anybody online?
I have a microphone, so I might take that prerogative whilst we wait for an
Bren.
online question.
Okay, yeah.
So UNets by construction are supposed to retain high resolution spatial information, right? That's why you have the skip connections. So I don't think it's an architecture issue. When we did some prototyping with downscaling, we found that what was missing was orography. When we put orography in as one of the inputs to the model, the quality of the output was vastly increased.
Yeah, we could definitely try that. Yeah, it's a stationary predictor field. Absolutely nothing wrong with it. Yeah, and I'm still a bit surprised that it doesn't retain. Well, we'll talk about it. Yeah, maybe you're right, because it's, if you don't have orography, maybe that's the honest answer. And if you have orography, maybe the refined version is the honest answer. Yeah, thanks.
Yeah, that's a good point. Okay, I think we need to, I think we need to move on. Is it a quick one? Okay.
Martin's very good. And my question is already asked by the, but I just wanted to say that I didn't get what kind of downscaling did you do? You took the 0.25 degree data from IMD, is it?
Yeah.
And then how much resolution you went? 2x or 4x?
Yeah, no, maybe I confused you with my comments on downscaling. This is not downscaling, right? This is post-processing. So the truth is actually, the forecast has a 12-kilometer resolution. The IMD has a 25-kilometer resolution. We actually coarse grain it. It's about getting rid of systematic errors on the 25-kilometer scales, and then we can recapture the 12, but we get the original distribution back. That's easy. Yeah, by spatial disaggregation. But it has nothing to do with downscaling. All I was saying is that UNet is usually used in the concept of downscaling. Now we're using it in the context of.
Yeah, I'm also using unit downscaling for forecasting as well. And as he suggested that we have to use more variable, and orography is one of the very important variable for downscaling.
I think we're going to try
Thank
that
you.
soon.
I will not take much time. Thank you. Thank you.
Okay, thank you. You can always continue discussions over lunch. Right, our next speaker is Patanayak. I know I'm probably still messing up these names, so please bear with me. I hope I didn't do too badly there. Right, we're looking at medium and extended range forecasts applications in disaster management. Is that right?
Yeah.
I haven't seen the slides come up yet. So yeah, I'll give you a 13-minute bell.
Okay, sorry. So very good afternoon. Already morning, many interesting talk were there by our US scientists. So this is I'm from Intermediate department. So I'll be talking about the practicality of our forecasting and how we are using this for the operational purposes. That's why I have added the word, the disaster management and early warning and disaster management. So as IMD is the operational agency, and we are responsible for all type of severe weather forecasting. And the mandate is that no severe weather should be undetected, and how the lead time should be sufficient for the disaster manager. For that, what the things are we doing, and what are the challenges that I will be discussing in this way, with focus on medium and extended forecasting, so that we will have some lead time for particularly severe weather time. Okay, just very quickly, the 2 minutes I will take. This is the monsoon pattern. So you know all the seasonal monsoon. There are pockets of west coast, all this high rainfall, and also the low rainfall belt over northwest India. But when we see the extreme rainfall, means heavy rainfall, very heavy or extremely heavy rainfall. So this is on climatologically, if we take the 50 years average, so these are the area is where we get more number of days with very heavy or extremely heavy rainfall. So all the central India and system forming and moving northwestward to over the and west coast and northeast India. So this is on the climatological pattern. But what is happening, if you take a different time scale, let us say the multi-decadal variability, yes, there is no significant changes, means no trend in the seasonal rainfall, but there are epochs are there. But if you see last 4-5 years, yeah, there are many peaks on the higher side, means above normal also there. So that is also interesting. And that if you want to see in the longer multi-decadal oscillations, yes, we are again different epoch, and now again we are going to little bit higher epoch that should last. So this is then with respect to operationally, this is from the operational data what we have obtained from IMD, let us say for 2013 to 2023, based on the actual station observations. So what is the frequency of extremely heavy, that is more than 20 centimeter, very heavy more than 12 centimeter, and heavy more than 7 centimeters. So all the three, and the miss that blue color is your the combination of all three. So there is an increasing trend that is noticed in last 15 years if you see operationally. So this type of increasing trend of heavy rainfall or extremely rainfall during monsoon season, it is great challenge actually, particularly for the early warning, and not only the early warning, and it is for the disaster management also. Okay, so then then this is leading to all flooding area and increasing flooding area, death also due to flood. Every monsoon season it is happening, and this is just a how based on the last number of years. So this is the thing. And recent last monsoon, each monsoon is unique. So I will highlight this monsoon. If you see, this is on the higher side, 108%. So above normal rainfall, you will not get any break type of situation here. So that means most of the days are above normal rainfall. There are pockets of July, August, and even September end also. We have vertical peaks that is more than normal. So day-to-day rainfall on country as a whole, if you are or central India, if you see, it is much higher rainfall on many of days. And this is resulting of there are a lot of systems were there. You can see it is contributing, even the one system that is also intensified into a cyclone and entered into Arabian Sea. So this type of system, when synoptic systems are there, it is contributing significant amount of rainfall. That's why as a result, you have seen the last 15 years, there is significant increasing. So what is this? In special distribution, if you see, special distribution, this is the very heavy rainfall during different months, June, July, August, September. And this is the extremely heavy rainfall during June, July, August, September, or last year. So if you see here, the red August, September, and even June, July is slightly less. That vary from year to year, but extremely heavy also. This is a low rainfall belt, actually Gujarat or Rajasthan. But if you see here, August, a lot of rainfall we have got because of the extremely heavy rainfall we have got due to the system movement. So this type of patterns are there wherever the low rainfall belt also are getting very extreme rainfall event that is leading to unprecedented flooding situation. So what it means? That means if you see the 5 years also, that frequency is increasing just 5 years. Total number of event heavy, very heavy, extremely heavy, and this is only extreme that is also increasing. So date year wise also these events are increasing, though there is no seasonal trend. So this lead to actually flooding. So this is large area. If you see this year flooding and all the states of the India, there are death due to flooding. In Kerala also landslide were there. So all these deaths are because of the flooding. There are other, of course, severe lightning, thunderstorm was also causing, heat wave also causing, but I am highlighting only with respect to the monsoon rainfall. So this is a great challenges that disaster risks are the increasing due to the increasing intensity and frequency of hydrometeorological disasters, in value of exposed element due to development and demographic expansion. So disaster risk management is a critical component of climate change adaptation. And in order to address this one, there are two aspects. One is multi-hazard early warning. Multi-hazard early warning, this is a under WMO, this severe weather forecast project is already there, while all national agencies are using all type of model inputs available for different parts of the world, and how we can improve the multi-hazard early warning. So that's why we are working on this thing, multi-hazard early warning, to have sufficient lead time. Second component, now it has started. The last year emphasized, the first workshop we conducted in December 2024 here, that is interoperability implementation. Means how it not only the forecasting is sufficient, lead time, of course, you have to go to impact estimation and interoperability, because sometimes severe flooding also causing death to the mining worker. Nobody knows that way whether the miners are inside the thing or that thing. So water will enter. So that's why interoperability means when we are issuing early warning, the forecaster, agriculture, water resource, miner, all these things, those who can utilize or those who will be impacted by this thing, they have to be communicated. They should be their products, your forecast or communicator, what you are communicating should be in that language also. That's why interoperability framework now WMO initiated, and now we are also going for that one. Multi-hazard early warning system interoperability. With this background, now how we are going for that thing, and I'll come to the background. So my focus here is the extended and medium range time scale. Let us say for any type of such type of event, means when heavy rainfall or this thing, how good at present we are, and what are the things we are doing, and what are the things we are lacking. So here we have a very good modeling system from starting from extended range here. If you see here, this is the thing. Okay, so we start, let us say extended range. Every week we are running this thing for 4 weeks work, generally forecast for 4 weeks. Then we come the multi-model. We have 6-7 models are there from different platforms. There we are using in the medium range time scale for particularly for addressing the heavy rainfall. We have our own couple model system, atmospheric modeling system, NCM and IITM also is here. That is also we are using. Then when we go to very short range casting or anything, we have the lighting data assimilation, EWRF, and high resolution rapid replay, that is for nowcast. Nowcast purpose also here. So how this temporary bidding and also spatial scale, we can go from higher to lower scale. So then this not only the forecasting early warning, but the extra you have to the information, the impact and information is very crucial, particularly the impact estimation. As I said, the not only the forecast accuracy, not lead time, even the impact assessment. That's why now with the information that has to be communicated, what are the likely impact. So now we are working on this one for our day-to-day operational purpose. So when we come to the extended range, let us say I start from the extended range. Every week we are updating the forecast product for 4 weeks. So this is the couple model, and we are running on the fly. So 16 ensemble member, hindcast and forecast. Then this all products are generated, cyclogenesis, temperature, etc. But I will focus on the heavy rainfall. This is the overall India scale. If you see 3 weeks, it is good, useful. Then agriculture purpose, 3 weeks also it is very useful. We can utilize this one. And this is the central India, that is also very significant. As you go through the smaller special, the scale is reducing. And state, I will come to the heavy rainfall of the last year. So this is the observed rainfall. If you see during the week from 1 to 8 August, that is contributed in Rajasthan area, Northwest India, and this is the 22nd to 29 August. If you look at here, means a very large entire belt here. That means wherever the heavy rainfall this year occurred. So this is the observed rainfall, very highly positive anomaly over this region. And when we see the forecast, what was the forecast for the real time in the extended range based on 31st July, this is the week 1 forecast, valid for the same period. Week 1 forecast, this is the week 2 forecast. And this is for the second event, this is the week 1 forecast and week 2 forecast. So if you look at this figure for 2 weeks, the above normal rainfall for next 2 weeks are it is indicating over the central India. That's how it will translate into actual occurrence of the extreme rainfall over this thing. That there we have to come to the medium and time scale. But this is how this extreme rainfall is predicted in 2 weeks in advance. I am not going beyond 2 weeks because the sufficient 15 days warning is sufficient for the disaster managers. Then unique case was the Kerala event. Kerala event was the 30th, 29th July. So that exceptional rainfall occurred over Kerala, led to the landslide and all these things, disaster, and many people, more than 300 people lost their life. So if I see this event operationally, how we have handled this or how we have communicated in the real time to the different disaster managers, because there are a lot of discussion, even the central level, the regional level, means how it was handled. So this so this is our forecast for that particular week actually. This is the week 2 forecast based on 18th July, and this is the week 1 forecast based on 25th July. If you look at this there is a heavy rainfall is reported here. That is week 2 forecast also. That's why we could able to communicate on 18 July itself. That means heavy rainfall is expected, and even in our impact also, if there are include what are the SOP there, if there are exceptionally heavy rainfall or very heavy rainfall, then what are the things like landslide, possible landslide, that indication was already there. And our regional center at the Kerala regional center also communicating at small. So they are using that our forecast. And this is the for the only state-wise forecast. So again, this is on 18 July, and this is on the week 2 forecast. So even the week 2 forecast where the event has occurred, so they have predicted actually above normal rainfall. Above rainfall over Kerala the week 2 based on 18. And this is the real time forecast on 19. So 25th July, so week 1 forecast also, it was communicated the above rainfall. And after that week 2, again rainfall was reducing. So that transition on smaller scale also, it was indicated. And due to this thing actually, our Met Center could communicate at least well in advance that there will be. So that we had sufficient warning was there. How then there was also 2024, lot of events have occurred. So if you see 2024, because the India is big or smaller, central India itself is a big, because now we need very smaller region. So we have restricted to 36 Met subdivisions. So 36 Met subdivision here, 8 events are there. Here also one Kerala event is also there. So 8 events. This is the actually observed rainfall for the total in the weekly, that particular week where our forecast is there. And this is the departure. percentage departure during that. That means this is the above normal departure, particularly that state is observed rainfall, and what are your forecast and what are your departure. So when we say extended forecast, week 1 and week 2 forecast, if you see week 1 forecast, everywhere it is large excess. This is our interpretation. Wherever it is a 50%, it is exceeding a large excess. Week 2 also it is matching. Only on 2 occasions it is normal. That means on the positive side for the normal. So that means that indication, even the if we see on smaller scale, we are getting up to some extent that event. Then this is a means 2002 case of one I'm showing here. Also there are 2 vertical peaks were there, and if you see these 2 cases, this was the rainfall observed rainfall, and week 1, week 2, week 3 forecast. So that's why this at least we up to 2 weeks. That's why we are using up to 2 weeks the active and break cycle. But with respect to the flooding event, 2 weeks we are restricting here. And this is a 2022 case. Then if you see here, this is also August was there, 5 to 11 August. So a lot of events were there during 1 minute. Okay, let me complete. So now in the coming to medium range time scale, we are using all 5 models, 7 model actually now to see handle this one. So this is one example I have. So let us say 2022, what I was showing in the extended range. This is the observed rainfall as per the classification. We are giving red color. Wherever it is hex reading, this is day 1 forecast, day 2 forecast, day 3, day 4, day 5. That means up to day 2, day 3 forecast, we are able to give this red color warning based on our model. This is the direct MME based product are available, and using that one, we are actually issuing the soft district level also warning, color code warning using this product. That's why when we go from extended range to medium range, even this scale, it is very useful. We are able to do this. And not only that, we are generating, this is the observed rainfall, and this is week 1, day 1 forecast, day 2 forecast, this is based on directly MME program. And at the regional level means our MET center, they are modulating this forecast, district level forecast, and they are reaching to that one. So that is the, wherever it is expected to over prediction, it is reducing. When it is under prediction, they are increasing. So this is the value added operational forecast are generated. And that's why it is there is an improvement in the forecast accuracy with last 5 years also. This is how 27% improvement in last 5 years during 2024, and missing rate is decreasing. So this is my last slide. So here my point is here that significant improvement in multi-hazard early warning and disaster risk reduction in recent years, leading to a drastic reduction in loss of life, especially due to cyclone and heat wave. That are there with cyclone and heat wave. But with respect to heavy rainfall, still the forecast accuracy has improved, the lead time has improved, but still there are a lot of work need to be done. So for that, though probability of detection of heavy rainfall event, skillful prediction of monsoon, active break phase, extended medium range target, but extremely heavy rainfall prediction remains still challenging. That's why now we are looking for the AI ML application, both the dual engine like NW models, lot of data are there, and artificial intelligence, so that further improvement it will be possible. And then the interoperability framework will be also in place. Then we will be able to reduce the disaster risk. Thank you. Thank you very much.
Thank you very much. That was really interesting. Any questions? I see hands. Yeah. I think we have time for one question. So if you have more.
Thank you so much, Chairperson. And thank you so much, the presenter. Very exciting, interesting presentation, because particularly for the last 3 days, you are the first presenter to use very applied term like the adaptation, response, and disasters. And I understood that you have the capacity to forecast up to the district level. If I'm correct. But you know, so the India has a diversity of terrain and geographical conditions, and the first response start at a very, very local level, even the municipal level or the village level, small water set level. So do you think that there is a you would be able to develop the capacity to make a practical forecast for the local level institution, so that they can help the local people, local institution to respond appropriately, timely, to respond to the disaster and adapt to the changing climatic condition, particularly the behavior of the monsoon? Thank you so much.
Yeah. So yeah, definitely the climate change causing this extreme rainfall event at local level. for the disaster, because one part is our part, one part is the early warning. That's why a lot of work is being done. Now, second part is the at the local level. Local level, we are integrating all the data, means from the local level, geophysical data, so all this also impact also estimation has to be there correctly. Then the disaster manager actually. So as I said, Kerala event, I was giving example. So accurately they need, means whether it IMD had predicted this or not. Miss, that's even Home Minister, I think Parliament also told. Yes, it was predicted, Miss something. But probably, so our, but when you go to the very location specific forecast, there are exceptionally heavy rainfall, 50 centimeter occurring. That if you, even if that you consider outlier, otherwise the miss slightly less rainfall amount, we are able to predict in well in advance. But still challenges, as I said, the improvement what we have done in cyclone or even the heat wave, that is more predictable and now well monitored system. But this is very exceptional cases are there, means the highly nonlinear system. So, but the development if we see in last 5 or 10 years, that is tremendous development have taken place. Hopefully in future, we will be able to achieve the requirement of the very small special scale or other users. That's what I can say. Thank you.
Yeah, thank you very much. Right, I think we're finished. So let's just thank Patanaik for his talk. Yeah, very good. Okay, so our next speaker is unfortunately not here, Snelat Turkey, but we therefore move on to the last talk, which is by Hasbur Rahman. Pronounced that any good? I don't know. On 45 years of ocean reanalysis. And yeah, 13 minutes or the bell might ring.
Slide forward this one. Okay. Good afternoon to all of you. First of all, thank you so much for IWM organizer for giving me the opportunity for presenting this work. I also thank my institute director, Dr. Balakrishnan Nair, to giving me opportunity for allowing me to come here, as well as Secretary Dr. M. Ravichandran, who's inspiring initially, whom I worked more than a decade before he left, moved out from INCOIS. So I'll be presenting this first ever, we produce these 45 years of ocean reanalysis based on GODAS. GODAS, you know, Global Ocean Data Assimilation System, which we run operationally in INCOIS, and we give the ocean analysis for the CFS initializations at here in IITM for the seasonal monsoon predictions. I thank all my co-authors as well as contributor for this work. So the motivation for this study is recently we published one paper in modeling Earth system and environment, where we showed this short reanalysis based on this MOM5 for 2003 to 2010, where we showed this we showed this reanalysis is even some kind of better than ORA S5, which is considered to be the best reanalysis product as of now. And also this based on older version of MOM 4P0D, which is running for this operational, that also is improved a lot for that. So this motivates us to make the longer term reanalysis products with help of collaborating with NCEP. So what is reanalysis? Of course, people knows many way. So reanalysis basically is a kind of methods to include models and observations, as well as this surface forcing using atmospheric model, and to make a most realistic ocean state for these climate studies, and many other applications are there, like climate change studies. Most important, these initializations for seasonal predictions model, and including here in IITM, and as well as many other research and development work. And very recently, as my previous speaker also told, that recently the AI/ML based models needs to be trained, and which is relying on mostly on most accurate reanalysis products. So that's why it's very important to make the most reanalysis products, particularly the ocean. There are limitations, of course. It's not the perfect we can make. There are many challenges for this, particularly these reanalysis products are not very good but near to the coastal regions, mostly due to the resolutions as well as the model physics. And also there are many other, this mostly uncertainties arises from the model errors as well as numerical assimilations method, observational data, and as well as atmospheric forcing, which is another one very important aspect for this. So in a nutshell, these are the ocean observing platforms is available over the global oceans. There are many multi-platforms are available, like this XBT, which is measure from ship course, and then this Argo, which revolutionize our ocean observing system, is in this is beginning of this century. And that is one of the, I'll show you how it is impacted this reanalysis as well as the different moorings, which is equatorial moorings. And what we do is ocean model we use, and we use these ocean observing systems, combine them, and then for using this ocean, this operational analysis, reanalysis products from atmospheric model, force this as a boundary conditions, and generate this analysis and reanalysis, which is used for different other applications to seasonal predictions models and ocean monitoring, particularly the climate signals like ENSO and all. So these are the currently available reanalysis products available recently as of now. Different operational centers produces this. ECO from NASA, Brand from BOM, Australia, SODA, which is one of the very widely used University of Maryland, produces this regularly. And then no, of course, NOAA and SAFE, which is very updated one. And then our things inquires Global Ocean reanalysis version 1, which is also released for public. I'll give you the details about that. And then ORA is 5, which is also, as I told, many studies shows that the best product as of now. There are different resolutions, then Mercator Oceans, Glossies, Sea Glows, and of course the Glossy also from UK Met Office. There are different timescale is available with different resolutions. And mostly if you see these are the products based from MOM as well as the this NEMO based model. These two groups, basically two group of model is using this. So coming to this model, it's basically the setup is same as what we are using for this CFS V2, except the model upgradations. This is the bathymetry we use and global domain. What is the model domain? Atmospheric force fluxes we use to run this 1979 to 2009 using CORE2, Coordinated Ocean Research Experiments, which is a widely used forcing fields for the global ocean modeling community. And but this, unfortunately, it was not there beyond 2009, which is basically as NCEP 2 corrected version of that. And then beyond that, we use the NCEP 2 reanalysis, data assimilations. We use the 3D bar assimilation system with a window of little bit, not a symmetric window as typically people use. We use the 6 days back to 10 days ahead and with a central date. And then we use temperature and observed temperature and salinity over the global oceans from all these observations, whatever available. And we surface boundary, we use the SST relaxation from ER SST with a 10-day relaxation time. And outputs are available from 1979 to 2023. And what you see is here in this below this one. Oh, okay. So this is what you will see is the daily temperature and salinity profile, which is goes into these assimilations. And there is, you see, before 2000, there is a hardly very minimum observational are available for this. And after 2000, only this quantum jump happened because of this Argo observations platform available. There is a quite a jump in this 2003 to 2006 in that period. What we found is after zooming it, what is the different basins it's contributed from this Atlantic. There are some observing platforms which stopped working, and this is the same data what we use for the NCEP also reanalysis. They are using for the little bit older version MOM 3 based, which is quite I mean older. This 1999 model. There are different physics and many improvement is there in MOM 5 now what we use. So this is couple of results, quick results we found it here, like what you see this SST, which is most important. And the top one is shows this NINO 3.4 SST, and it sees you see the internal variability is well captured, except some of the peaks. And here also you can clearly see is before 2000. The era which that lot of observations are not available, where there are some mismatches are there. However, 2000 onwards, this is almost matching well, very well. And this is the Bay of Bengal average over Bay of Bengal also internal variability is very well captured. And So this is a special comparison. What you see is the top one is reanalysis, and this is OISST. OISST is kind of independent observation. You can say we are not relaxing OISST. We used ERSST for that. So if you see these two special observations, special comparison, if you don't say, if you remove this title, it's very difficult to which one is observation and which one is reanalysis. However, if you plot the biases, there are some large biases is seen in the Southern Ocean belt, and of course this is up to 1998 to 2009 average bias, and this is beyond 2010 to 2019. You can see very drastic improvement in the biases even in this region also. Why is it? Because there's a lot of observations comes. Virtually there was nearly a near absence of observations in this part of this southern part of global ocean. So another one thing is like subsurface, yeah, the Eastern Pacific subsurface temperature, where is thermocline basically is the signal of our ENSO, which is very important. And we saw that 95-meter depth temperature evolutions from 1979 to till 2023 is compared with the EN4 observations. You can see is very one-to-one match almost, and there are super El Nino kind of thing 1997, 2015, 16, as well as 1982. That one, as I told you, there is a lot of there is no observations available, and that's maybe the reason which is not able to capture. And this is the similar thing which you see is the average of entire Nino 3.4 region, and that is also will capture all this interval variability. This is when you compare to the all other centers SST available from this. This is 2012 to 2017, which is the common period used. This is RMAC using COBE, another one SST, which is very widely used for the climate signals. And where you can see mostly all are mostly is except this ECO, which is large biases or large errors are there near to the coastal regions, but in the IGORA, which is this our products, is almost matching. I mean, much errors are much reduced even compared to Glory, particularly the southern part of this. Of course, this Somali region in the most of the models also have the large errors. This is also the perennial problem in modeling in the coastal regions. This is the correlation coefficient. Similar results also you can found the high correlations in almost all these models, which is IGORA is also not exceptions. There are some slight reductions in this equatorial belt, but GODAS INSEP GODAS has little bit lower correlation over these regions. We're trying to identify because probably it's some of the forcing or some other regions could be the reason for this. We are trying to identify this. And this is one of the, as you know, the Southeastern Arabian Sea is one of the very important region for this onset of monsoon, where this very high temperature, high SST occurs during the pre-monsoon May on April-May, where it's attained more than sometime 31, 32 degrees centigrade, and it's also named as the mini warm pool. And it is a test bed to see how this reanalysis products capture this. And we use this AD09 from our own observing system, Omni buoy, which are there in different other locations as well. But we use AD09 for this, and you can see the 2012 to 2018, 17, how this evolutions. There are although this seasonal cycle and interannual variability is well captured, but most of the all these reanalysis products, but there is inter reanalysis products spread is still high, and this is a peak May which attains the maximum temperature, and which is you see the IGORA, which is our products, is almost matching the black, which is observations 8009. And there are cooling, which is July August cooling is not able to much model reanalysis are showing much cooler in than observations many models, but this IGORA is also very close to these observations what we observe. So this earlier we used the MOM4P1 as well, which is this is documented in this paper, which is we found this even we compared all the even observational based SST products as well, which came out to be reanalysis based SST, even somewhere performing better than observation based synthetic analysis as well. So this is coming to the surface salinity, how it looks about the biases and RMAC. What you see is here the entire domain 1979 to 2022 biases. There are large biases exist over this belt in southern belt, southern the oceans as well as the equatorial belt, Pacific. And they, if you segregate in two parts before 2000 and after 2000, you can very clearly see these biases are almost gone in all these two of the basin, except the coastal region, which is already present in everywhere. Though, so the reason behind this, and these similar things also we found is RMSE as well. So the reason behind, as I told, is this: virtually there is almost near absence of all observation beyond this beyond southern part of hemisphere. But if you see 2020 or 2001 to 22, virtually all part of ocean is observed, observations is available. Okay, so this is RMSE, which is also compared well, and the subsurface temperature, as I told you, is very close to EN4 observations, which is ERA or ORISE 5 is little bit high in the most of the other climatic regions, and this is subsurface salinity. Similar results also found here as well. And then one of the Atlantic meridional overturning circulation, which is the most climatic event, and there are many studies also show the AMO also affect the Indian monsoon. You see here this transport AMOC is very well captured by this IGORA compared to the rapid observations, which is there in 26.5. We also saw the glossy is little bit off than observations what we see. If you see the mean of the subsurface, there is a peak and 1,000 meter, which is well captured. And these figures also show how these observations are actually basically contributing to the peak of this magnitude. And another one thing is like we saw the another one sensitivity experiment. If you use the 10-day assimilation window and minus 6 to 10 days ahead, there is not much differences. No assimilation is not able to capture this strength as well. And this is IGORA is available from our website. And last 3rd February, our Inquiries Foundation Day, this product was launched by Secretary as well as DG CSIR, and this is available in LAS server. And this is the summary. As I already told many things, most of the things is other operational centers are producing this, and we also joined this elite club and this for the first time, and many other things I already just described. And this is one of the things which is we are trying to write a comprehensive paper on that, how this comparing to all the other IGORA and variability. That's it. Thank you so much.
Thank you very much. Have we got, okay, Dr. Krishna?
Yeah.
Have we got a microphone?
Thank you, Dr. Herman. Very nice talk.
Thank you so much.
See, the salinity profiles after 2010, there was a big decrease in one of the number of salinity profiles.
Yeah.
So how does it impact your salinity after 2010?
So that affected in Atlantic. Those observations, what you saw, initially when we saw the global ocean, then we tried to segregate where is coming from that.
Yeah.
So this is basically coming from Atlantic, some of the buoys and
so
all.
it may have a big impact on your AMOC. Because you also showed the strength of the AMOC.
If
you are not assimilating salinity.
No, we are assimilating everything, but whatever available, there is
numbers have come down, right?
Yeah, numbers have come down, but after that it's quite stable. It's not that after that was peaked. If you see the curve, it is more or less all the other basins also. There are certain epochs, it's gave more number of observations in Atlantic. That's why
So how about the Bay of Bengal? Are there enough salinity profiles showing?
Yeah, Bay of Bengal, we didn't look on details about all this region wise. We're trying to make all this, how this impacted. But certainly there are other papers what I published earlier. If you see the thermal inversion, if you using the salinity observations, assimilations, only you are able to pick this thermal inversion, even in these GODAs, whether it's anywhere. If you are not using observed salinity, this thermal inversion is absent.
Thank you.
Yes, sir.
Okay, any more questions Or are we ready for lunch? Is there one more? I know that there's an announcement about the early career session later, so Oh, there is an online question. Can you read that? Have you got it on your screen?
Yeah. What is that? What is that question actually?
Yeah, I'm trying to.
Huh?
Is it a comment? It looks more like a comment.
It's a
actually.
comment, it's not a question, I
Okay.
think.
All right.
Yeah.
Thank you.
Yeah.
Okay. So announcement.
Okay.
Okay. Right.
So it's okay. I can go now. Okay.
I request now Dr. Hindumati to thank our session chair with a memento. As we conclude this session, I would like to extend my heartfelt gratitude to all the esteemed speaker, session chairs, and attendees for their valuable contribution. And after this, there are few announcements. Just 1 minute I'll take. The session, I would like to remember that session time tomorrow is the morning has been moved up by 10 minutes. So I request you to please gather here around 8:50 a.m. Indian Standard Time. And today we have poster session just after lunch from 2:15 p.m. IST at Rituram. And lunch, we can disperse for lunch now. And lunch is arranged at basement of this hall and IITM guest house. Thank you. No, now it only poster session is there. After that, early career research. Okay, yeah.
So I have an announcement to make for Lian and Lie about area session. It's going to begin at 4 p.m. sharp here in this auditorium. So even though even the ECRs who have not registered before are welcome to join. And for the seniors and super seniors, we are also welcome to join between 4 and 4:30 and after from 5:30. Thank you.
झाला आता संपलंच संपला आता